Have you ever seen the gigantic scale of military megaprojects on our planet? From hidden military bases to bunkers that could fit hundreds of thousands of people, these projects were made to protect nations for generations. Today we'll investigate the biggest military megaprojects and show you projects you didn't even know were keeping you safe. Underneath 650 feet of Pennsylvania granite, the Raven Rock Mountain Complex, also known as Site R, stands as one of the United States' most fortified underground military installations. Located near Blue Ridge Summit, along the Pennsylvania-Maryland border, it was built during the early 1950s as a direct response to Cold War tensions and the looming threat of nuclear attack. Construction began in 1951, authorized by President Truman, with the explicit goal of creating a hardened alternate command center for the Department of Defense. If Washington, D.C. were ever incapacitated by a nuclear strike, key military operations could immediately shift to Raven Rock. The complex was completed in 1953 and activated under the supervision of the Army Corps of Engineers. The facility consists of a vast underground structure spanning several acres, with over 5 miles of internal roads. It contains 3 primary chambers, each roughly the size of a large aircraft hangar, dug directly into the mountain. These chambers house communications infrastructure, command centers, dormitories, offices, power systems, and storage facilities. The facility is capable of supporting up to 1,400 personnel in a fully sealed environment, with self-sustaining water reservoirs, diesel power generators, and air filtration systems designed to handle nuclear, biological, or chemical contaminants. Access is controlled through a heavily guarded portal sealed by 5 34-ton blast doors, each engineered to withstand nuclear shockwaves. Inside, everything from secure satellite uplinks to war room-level operations facilities remain on constant alert. The complex is linked by encrypted communication lines to the Pentagon, NORAD in Colorado, and other key defense installations, forming part of the larger U.S. continuity of operations plan. Site R is operated primarily by the U.S. Army, though it also supports joint military command functions involving the Navy, Air Force, and Marines. During the Cold War, it was directly tied into the National Military Command System and included in war game simulations for full-scale nuclear conflict. The facility has served as a communications relay, emergency response center, and alternate National Military Command Center. In modern times, Raven Rock continues to be staffed 24/7 and is one of the designated relocation sites for top military leadership. While it was originally envisioned as a Cold War contingency, it remains active today in the face of evolving threats including cyber warfare, EMP attacks, and large-scale terrorism. Its infrastructure has been upgraded repeatedly to include hardened digital systems and secure data nodes that integrate with national command networks. Though highly classified, occasional leaks and declassified documents have confirmed that Site R includes advanced telecommunications suites, a full medical center, armories, and a detention facility. It also has multiple escape tunnels, helicopter pads on the surface, and redundant logistical pathways for long-term isolation. At the height of the Cold War, while the world stood on edge beneath the specter of nuclear annihilation, the United States embarked on one of its most ambitious military engineering projects, hollowing out the core of a granite mountain to build a fortress that could survive the end of the world. This became the Cheyenne Mountain Complex, a hardened command and control installation designed to absorb the unimaginable and keep operating. Excavation began in 1961 in Colorado Springs, Colorado, on the eastern slope of the Rocky Mountains. Engineers drilled and blasted through nearly 700,000 tons of solid granite to carve out a vast internal network of chambers, tunnels, and infrastructure. The granite was selected not for beauty, but for density and stability. Its shock-absorbing properties were critical in the event of a nearby nuclear blast. Inside, 15 independent buildings were constructed, each mounted on over 1,300 steel springs, capable of swaying independently to absorb seismic shock. These buildings were not simply placed on bedrock. They were suspended within the mountain's hollowed core like floating islands of steel and concrete, isolated from the earth to maximize survivability. Each spring was rated to deflect up to 18 inches in any direction. The complex was designed to withstand a 30-megaton blast as close as 2 kilometers away. Blast doors weighing 25 tons sealed the entrances, and every major system inside had multiple redundancies. Air intakes were filtered through massive banks of scrubbers to remove radioactive, chemical, or biological contaminants. The water system drew from an underground reservoir, and backup diesel generators could keep the facility running independently for months. The construction took 6 years and involved thousands of workers, operating under extreme security and secrecy. Much of the interior concrete was poured under tightly controlled conditions to meet military specifications for strength and radiation shielding. Electrical systems were buried and shielded to resist electromagnetic pulses, and communication lines were hardened to maintain contact with key command centers like the Pentagon and NORAD's other facilities. By 1966, the Cheyenne Mountain Complex was fully operational. Its primary mission was to serve as the command center for NORAD, the North American Aerospace Defense Command, tasked with monitoring and responding to any missile threats against North America. Radar feeds, satellite data, and early warning systems all converged here, where military analysts tracked potential nuclear launches in real time and coordinated defensive responses. The layout of the complex includes over 4.5 acres of internal floor space. More than a mile of tunnels connects operations centers, data rooms, dormitories, dining facilities, and even a medical bay. Every piece of equipment was selected for durability under catastrophic conditions, and everything from door frames to wiring was built with the expectation that it might one day be tested in the most extreme scenario imaginable. Few megaprojects embody Cold War secrecy and Arctic engineering, like Norway's Olavsvern submarine base, an underground naval facility tunneled directly into a mountain just outside Tromsø, north of the Arctic Circle. This hidden fortress was conceived at the peak of NATO's strategic concerns in the North Atlantic and took decades of planning, excavation, and military coordination to bring into reality. Construction began in the late 1960s, driven by NATO's urgent need for a hardened naval base in Scandinavia to monitor and counter Soviet submarine movements in the Norwegian and Barents Seas. Olavsvern was designed from the outset to support both surface vessels and nuclear-powered submarines, offering them a completely secure and concealed operations hub within Norway's extreme northern geography. Engineers excavated over 25,000 cubic meters of solid granite to build the complex. The core of the facility is a massive internal dry dock, 300 meters deep into the mountain, capable of housing several submarines at once in total secrecy. Entry was via a camouflaged sea tunnel, nearly invisible from aerial or satellite reconnaissance, allowing vessels to slip in and out without detection. The entire complex was built with one purpose: survivability under sustained military threat. The mountain provided natural shielding against conventional and nuclear attacks, while internal blast doors and reinforced corridors added additional layers of protection. The dry dock could be sealed completely from the outside, and pressure systems maintained stable conditions even in the event of chemical or nuclear fallout. Inside the mountain, over 13,000 square meters of operational space was carved out and fortified. This included command and control rooms, crew quarters, repair workshops, fuel and weapons storage, and climate-controlled chambers for advanced sonar and electronic systems maintenance. The facility was fully self-sustaining, with independent power generators, freshwater reserves, and secure communication lines linking it to NATO's command network. Construction was carried out under extreme environmental conditions. Winter temperatures regularly plunged below freezing, and the surrounding fjords presented major logistical challenges for transporting materials and machinery. Specialized tunneling equipment had to be shipped in and adapted for Arctic rock conditions, while crews worked in shifts around the clock to meet strategic deadlines. The base was built not only to hide submarines, but to actively service and rearm them for extended missions. Fuel depots were constructed with double reinforced walls, and weapon storage areas were shielded against electromagnetic pulse effects. The internal rail systems moved torpedoes, spare parts, and equipment deep within the base without reliance on outside handling. Everything was streamlined for rapid turnaround under wartime conditions. Strategically, Olavsvern gave NATO forward positioning capabilities near Russia's northern fleet bases on the Kola Peninsula. Submarines stationed there could shadow Soviet movements, gather acoustic intelligence, and act as a deterrent in a theater where control of the Arctic sea lanes could shape the outcome of a global conflict. The level of investment in the base reflected the military significance of the High North. At its peak, Olavsvern was staffed by hundreds of naval personnel, including engineers, weapons technicians, and communications officers trained for cold weather warfare. It remained one of NATO's most classified assets throughout the Cold War, largely unknown even to much of the Norwegian public. What makes Olavsvern unique among submarine bases is not just its concealment, but its integration with the landscape. Unlike visible dry docks or floating depots, this installation was invisible until you were inside it. It combined Arctic geography, naval warfare, and fortress-level engineering into one seamless warfighting platform. Even after its deactivation in the early 2000s, the facility's infrastructure remains intact, ready, if necessary, to be reactivated for a new era of geopolitical tension in the Arctic. As competition over the polar regions intensifies, Olavsvern stands as a reminder that military megaprojects are often not just about weapons, but about geography, silence, and the ability to vanish beneath stone. Hidden beneath one of the world's most populous cities lies a military megaproject so vast it was once rumored to span hundreds of square kilometers. Known simply as the Underground City, this Cold War-era labyrinth beneath Beijing was a massive civil defense initiative, an entire subterranean metropolis designed to shelter millions of civilians and military personnel in the event of a nuclear conflict. Construction began in the late 1960s, at the height of tensions between China and the Soviet Union. Fearing an imminent Soviet nuclear strike, Chairman Mao Zedong ordered the creation of a vast underground shelter system that could serve as a fallback infrastructure for national survival. Officially called Dixia Cheng, the network was built largely by hand, using picks, shovels, and sheer manpower from Beijing's civilian population, including teenagers and retirees enlisted through Mao's mass mobilization campaigns. The underground system stretched for over 30 kilometers, connecting major government buildings, military, command posts, residential neighborhoods, and industrial zones beneath Beijing's streets. Some estimates suggested the full scale reached nearly 85 square kilometers at its peak, though much of that remains classified. The tunnels were built at depths ranging from 8 to 18 meters below the surface, reinforced with concrete walls and vaults to withstand air raids and limited nuclear blast effects. More than just tunnels, the complex was built as a full-fledged backup city. It included sleeping quarters, hospitals, food storage warehouses, classrooms, factories, and even theaters, all designed to function in isolation for months if surface life became uninhabitable. Independent water wells, air filtration systems, and power generation units were embedded throughout the structure to support long-term occupation. Ventilation shafts were camouflaged across Beijing, often hidden behind fake buildings or disguised as ordinary street features. The project's primary military function was continuity of government. In the event of a nuclear exchange, high-ranking officials, military commanders, and key personnel were to retreat into the network, from where they could maintain communication, organize civil defense, and direct counterattacks. The tunnels were also wide enough to allow small military vehicles and supply convoys to move underground, keeping logistics flowing even under bombardment. Much of the engineering followed the Soviet model of deep defense bunkers, but was adapted to the soft, clay-heavy soil beneath Beijing. To counter groundwater intrusion and soil shifts, crews installed thousands of tons of rebar and laid drainage pipes throughout the tunnel floors. In some areas, double reinforced ceilings were used to provide additional shielding against radiation and collapsing debris. The workforce was enormous. Reports suggest more than 300,000 civilian laborers participated in the digging over the span of a decade. Coordination was directed by Military Engineering Corps, working closely with local Communist Party committees, and secrecy was paramount. Most workers were never told the full extent of what they were building. Though the Cold War threat that prompted its construction faded, the underground city remained partially operational into the early 21st century. Segments of the tunnel network continued to serve as military installations and civil defense shelters, while others were sealed off or repurposed. Some sections were briefly opened to tourists in the early 2000s before being shut again, possibly due to ongoing military use or modernization. The underground city exemplifies a distinctly Cold War logic. Prepare not just to fight, but to survive, rebuild, and reassert control from beneath the rubble. It was not a mere shelter. It was an engineered civilization beneath a capital, a megaproject designed to preserve command, culture, and cohesion during total war. It began not with a single building or base, but with the largest American military construction project undertaken overseas since the end of World War II. Camp Humphreys, located in Pyeongtaek, South Korea, evolved from a modest airfield into the sprawling nerve center of U.S. military power in Northeast Asia, a transformation that required nearly 2 decades of relentless engineering, logistics, and international coordination. The expansion was initiated in the early 2000s as part of a strategic realignment between the United States and South Korea. The goal was to relocate the majority of U.S. forces from their vulnerable position in Seoul, just 40 miles from the DMZ, to a more defensible location farther south. Camp Humphreys, already housing a small contingent of U.S. personnel, was selected as the anchor site for this megaproject. The scope of construction was immense. Over 3,500 acres of land had to be secured, making it the largest U.S. military installation in the world by size. This required the relocation of several nearby South Korean villages, the rerouting of major roads, and a complex land reclamation process to prepare the site for development. The total area more than quadrupled, turning the base into a small city engineered for permanent, high-capacity occupation. More than 650 buildings were constructed, including headquarters for U.S. Forces Korea, family housing towers, barracks, schools, hospitals, logistics hubs, and training facilities. The site was master-planned with the expectation of housing over 35,000 people, including soldiers, civilians, and their families. Infrastructure included not just military assets, but complete civilian support systems, utility grids, water treatment plants, retail centers, and even fire stations. To ensure uninterrupted operations under wartime conditions, the base was built with hardened command bunkers, redundant power supplies, and secure communication systems linked to the wider U.S. Indo-Pacific Command network. Military logistics facilities included armored vehicle motor pools, aerial drone hangars, ammunition depots, and helicopter landing zones, all constructed to withstand both conventional and asymmetric attacks. One of the project's biggest engineering challenges was building on previously undeveloped and flood-prone land. Massive drainage systems were installed, along with deep foundations for major structures. Environmental impact mitigation required advanced soil stabilization and water diversion techniques to accommodate the region's heavy seasonal rains. Construction was overseen jointly by the U.S. Army Corps of Engineers and South Korea's Ministry of National Defense. At its peak, more than 17,000 workers were involved in daily operations, using heavy equipment and modular assembly techniques to accelerate progress. Prefabricated components were shipped in bulk from both domestic and international suppliers to meet deadlines and cost targets. The base is structured with a dual-purpose design philosophy: readiness and endurance. Warfighting infrastructure is integrated seamlessly with daily life systems. The command centers are located beneath reinforced buildings, while key logistical routes are protected by anti-vehicle barriers and surveillance perimeters. Internal road networks, emergency evacuation paths, and refueling points are all planned with conflict scenarios in mind. Strategically, Camp Humphreys is more than a relocation. It represents a long-term geopolitical bet. The base gives the United States deep operational reach into the Korean Peninsula, China, and the broader Indo-Pacific region. It acts as a launch point for rapid deployment, intelligence coordination, and allied joint operations, all while sitting well beyond immediate North Korean artillery range. The megaproject was funded largely by South Korea, covering roughly 90% of the multi-billion-dollar cost as part of the country's defense cost-sharing agreements. This level of investment underscores the strategic importance both nations place on the site, not just as a military base, but as a symbol of enduring alliance. Hidden beneath the chalk hills of northern France, the fortress of Mimoyecques was one of Nazi Germany's most audacious military megaprojects, an underground artillery base engineered to bombard London with superguns from across the English Channel. Unlike V-1 flying bombs or V-2 rockets, this project relied on mechanical precision, underground fortification, and industrial-scale excavation to build a weapon system never before attempted in modern warfare. Construction began in 1943 under the code name Bovorhaben 711, following Hitler's directive to develop a massive fixed artillery installation capable of delivering continuous fire across 160 kilometers. The site was chosen for its geology. Chalk cliffs near the coastal town of Landreton-le-Nord offered easy tunneling, high elevation, and direct targeting alignment with London. The fortress was to house the V-3, a fixed-position supergun that fired projectiles at extreme velocities using multiple explosive charges along a long barrel. To make this possible, German engineers tunneled vertically into the hillside and constructed 5 inclined shafts, each 130 meters long, angled toward England. These shafts were meant to house multiple V-3 guns, with each barrel embedded into concrete-lined tunnels reinforced by steel supports. The design called for a rate of fire of up to 1 shell every 6 seconds once fully operational. Each projectile was small, but intended to be fired in such high volume that London would be under near constant bombardment. The weapon's strength wasn't in its explosive yield, but in the psychological and logistical strain of sustained remote artillery assault. Fired from a mountain fortress no aircraft could easily destroy. The entire complex required over 30,000 cubic meters of material to be excavated, using forced labor from occupied territories. Dozens of auxiliary tunnels were carved to connect command centers, ammunition storage bunkers, power rooms, ventilation shafts, and rail lines to transport shells to loading points. A narrow-gauge railway system ran directly into the base, allowing munitions and building materials to be moved without exposure. Protection was a priority. The fortress was buried beneath up to 30 meters of rock and concrete in some places, with blast-resistant doors, anti-aircraft installations on the surface, and redundant access routes to allow continued operation during bombing raids. The design integrated underground living quarters, operations centers, and machine rooms to sustain long-term usage under siege conditions. One of the biggest challenges during construction was the sheer complexity of the V3 weapon itself. Each gun was composed of a series of secondary combustion chambers set at intervals along the barrel, timed to detonate in sequence to accelerate the shell as it moved forward. This required extremely precise engineering, complex ignition systems, and meticulous barrel alignment, all of which had to be installed underground in tight quarters, under the threat of constant Allied surveillance. As Allied bombing intensified in 1944, the Germans accelerated work. They diverted resources and labor from other V-weapon sites in a desperate bid to bring Mimoyecques online. But the fortress was never completed. In July 1944, a series of massive Allied air raids, culminating in a strike by 12,000-pound tall-boy bombs, caused partial collapses and rendered the gun chambers unusable. German forces abandoned the site before it ever fired a shot. Despite its failure, the fortress of Mimoyecques remains one of the most extreme examples of military engineering ambition during World War II. It was not just a weapon site. It was an underground artillery factory, fortress, and command center carved into a mountain with the singular goal of altering the course of the war through mechanical saturation bombardment. Rising from Estonia's pine-covered plains near Tapa, Camp Reno represents one of NATO's most forward-deployed military megaprojects, engineered to support rapid reaction forces at the doorstep of Russia. This base was not built as a symbol, but as a highly functional logistics and combat hub, constructed to sustain prolonged operations in a high-threat environment. The strategic logic behind Camp Reno is clear. Estonia shares a direct land border with Russia. In the wake of renewed geopolitical tension in Eastern Europe, NATO required a hardened, rapidly deployable footprint on the eastern flank. Camp Reno was designed to host rotating multinational battle groups under NATO's Enhanced Forward Presence framework, enabling a permanent Allied presence without formal basing agreements. Construction began in the mid-2010s as part of a multi-phase infrastructure expansion program. The site was selected for its proximity to both rail and road arteries, as well as its access to the nearby Tapa military training area. Estonia's largest, allowing for live-fire exercises and armored maneuver drills within minutes of the base perimeter. Engineers laid out the facility with modular expansion in mind. Pre-stressed concrete foundations were poured for over 100 buildings, including barracks, armored vehicle shelters, logistics warehouses, dining halls, ammunition storage bunkers, and maintenance depots. Many of these structures were prefabricated in segments to accelerate construction timelines and reduce supply chain dependency. Vehicle infrastructure was prioritized. Camp Reno includes reinforced roads capable of supporting tanks, IFVs, and heavy artillery under all weather conditions. De-icing systems were installed on key pathways to ensure mobility through Estonia's harsh winters. Fuel depots were built with dual-hardened containment systems, allowing the refueling of armored units on site without external support. The camp's power grid includes redundant diesel generators and battery arrays. Electrical wiring was embedded with EMP-resistant shielding, and communications were integrated into NATO's secure digital backbone. Satellite uplinks, encrypted fiber lines, and field-hardened server rooms were added to ensure uninterrupted command and control capabilities. Each barracks block is fitted with internal NBC filtration systems. Heating systems are fully winterized, with underground insulation around all water and sewage systems to prevent freezing. Tactical operations centers are located in reinforced concrete bunkers partially submerged for added blast protection. Water security was a key challenge. Engineers drilled deep bore wells and installed purification systems with triple redundancy, ensuring a clean water supply even during siege or isolation scenarios. Wastewater is processed on-site in a closed-loop treatment facility, compliant with NATO environmental standards. The base also includes a secure arms depot with access-controlled vaults, shock-proof internal walls, and fire suppression systems that operate independently from the base grid. Ammunition storage was built with blast relief tunnels, angled shafts designed to vent any accidental detonation away from personnel quarters. Camp Rito's design includes pre-surveyed landing zones for NATO helicopters and temporary pads for vertical lift drones. The outer perimeter is protected by layered defenses, anti-vehicle trenches, motion detection fencing, infrared surveillance, and pre-positioned rapid response points for mounted patrols. While multinational forces rotate through on a regular basis, primarily British, French, and Danish units, the camp is operated in close partnership with the Estonian Defense Forces. Every system, from vehicle compatibility to radio frequencies, was built for interoperability with Allied forces from the outset.
In Jefferson County, the construction of the Denver Water Pipeline presents a quintessential example of complex underground utility installation in a mixed urban-suburban terrain. This pipeline, intended to convey treated water from regional reservoirs and treatment plants to distribution points across the Denver metro area, involves both large-diameter transmission mains and smaller branch lines. Its alignment must traverse roads, residential neighborhoods, open space, and utility corridors, each with its own set of engineering and logistical constraints. The pipeline installation begins with careful route surveying and subsurface utility engineering to identify conflicts with existing buried infrastructure such as gas lines, sewer mains, telecom conduits, and electrical ducts. In areas with high congestion or limited right-of-way, trenchless methods like horizontal directional drilling or jack and bore are used to pass beneath obstacles without open trench excavation. Where trenching is feasible, crews excavate in controlled segments, typically 30 to 50 feet at a time, using excavators with trench boxes or shoring systems to prevent collapse. The pipe sections, most commonly made from ductile iron or steel with cement mortar lining, are staged in laydown yards prior to installation. Each section is cleaned, inspected, and fitted with gaskets or welded depending on the joint type. For steel pipe, field welds are performed and non-destructive testing, often ultrasonic or radiographic, is used to verify joint integrity. After pipe placement, granular bedding and backfill material is compacted in lifts around the pipe envelope to prevent settlement or stress concentrations. A critical component of the project is maintaining hydraulic integrity across varying topography. Air release valves, blow-off assemblies, and thrust blocks are installed at high and low points or at directional changes to manage internal pressure and prevent movement. In steep areas, anchor blocks are cast in place using reinforced concrete and keyed into bedrock when necessary to resist pipe surges and expansion forces. The pipeline's internal coating is selected for corrosion resistance and to meet potable water standards, while the exterior is often protected by polyethylene wrap or epoxy coating. Crossing major roadways or waterways introduces additional design considerations. Steel casing pipes are used for board crossings under highways, with the carrier pipe inserted inside and supported on skids. Where the pipeline intersects drainage channels or creeks, it is often supported on pile-driven piers or encased in reinforced concrete to protect it from scour and erosion. Each crossing type is engineered with detailed hydraulic analysis to ensure no negative impact to surface water flows or floodplain capacity. Tie-in work to existing systems is executed during off-peak water demand hours, requiring temporary bypasses and pressure monitoring to prevent service disruption. All connections are hydrostatically tested prior to being placed into service, with pressure held for several hours and monitored for any loss or leakage. Once the pipeline is confirmed as watertight, it undergoes chlorination and flushing procedures in accordance with public health standards before being activated. Restoration of disturbed surfaces, including streets, sidewalks, and landscaping, is conducted under strict municipal specifications. Asphalt trench patches, concrete curb replacements, and native seeding in open space areas are carefully sequenced with utility completion to minimize community impact and ensure long-term site stability. Seen from a systems integration perspective, the QLine streetcar in Detroit represents a complex urban rail deployment that had to harmonize modern transit engineering with a dense, pre-existing streetscape. Unlike heavy rail or subway systems that benefit from dedicated rights-of-way, this streetcar line operates in mixed traffic along Woodward Avenue, requiring careful synchronization of vehicle operations, traffic signals, curbside access, and embedded infrastructure. The construction process began with extensive utility mapping and relocation. Since the corridor hosts decades of legacy infrastructure, gas, water, telecommunications, and electrical, the design-build team initiated ground-penetrating radar scans, potholing, and as-built analysis to identify conflicts. Where utility conflicts arose, crews executed trench excavations and coordinated shutoffs to reroute lines or deepen their burial beneath the projected slab track. These relocation efforts had to occur in tight time windows to avoid disrupting the urban core, with temporary road decking installed to maintain traffic flow during phased excavation. Track installation followed a slab track design, where continuous welded rail is embedded in reinforced concrete. To ensure vibration and noise isolation, each rail sits within elastomeric boots surrounded by flowable grout and high-strength concrete. This floating slab assembly reduces the transmission of mechanical vibration into adjacent structures and limits maintenance demands from thermal expansion and vehicle impact. Steel reinforcement within the slab was laid in grid patterns and connected to dowels anchored in expansion joints every several dozen feet, allowing for structural continuity while accommodating thermal cycling. Embedded in the track bed are induction loops for vehicle detection, signal actuation circuits, and grounding wires for stray current mitigation, especially critical given the electrified system. The QLine uses an overhead catenary system to power its vehicles, which required the erection of catenary poles and the tensioning of contact wire at a precise height and stagger. These poles, founded in deep caissons drilled between underground utilities, also support street lighting and traffic signal heads in a combined pole design to reduce streetscape clutter. Station platforms were constructed at sidewalk level, but raised slightly to allow near-level boarding, with ADA-compliant ramps and tactile warning strips installed along platform edges. Each platform integrates real-time passenger information displays, emergency call boxes, and prefabricated canopies mounted on spread footings beneath the concrete platform surface. Coordinated with the signal control system, these stops are geo-fenced to allow priority requests at intersections, giving approaching streetcars limited signal preemption to maintain headways and schedule adherence. The vehicles themselves, housed in a dedicated maintenance and operations facility at the line's terminus, are bidirectional and equipped with low-floor designs. These articulated units include onboard diagnostics, regenerative braking systems, and GPS-based location tracking. The maintenance building was constructed with embedded track pits, overhead crane rails, and specialized lifts to allow undercarriage inspections and wheel truing operations. System commissioning involved several stages: overhead wire energization, vehicle clearance testing, dynamic braking trials, and integrated traffic signal tuning. All systems, including communications, fare validation, and emergency override functions, had to be stress tested before passenger operations commenced. Tangled at the heart of Reno's freeway network, the Spaghetti Bowl has long been a nexus of intersecting routes, and the ongoing reconstruction project aims to untangle congestion while improving safety and capacity. The engineering challenge begins with phasing, keeping traffic flowing on both Interstate 80 and US Route 395, while major portions of the interchange are rebuilt. This requires carefully staged construction zones, temporary lane shifts, and a progression of work that avoids full closures wherever possible. The project involves replacing and reconfiguring multiple flyover ramps, each supported by a combination of cast-in-place reinforced concrete piers and precast concrete girders. Foundation crews first install drilled shafts deep into the underlying alluvial soils, using casing to stabilize the boreholes before placing reinforcing cages and pouring concrete. Above-ground piers are designed for both vertical load-bearing and lateral resistance to seismic forces, given the region's proximity to fault lines. One key focus is increasing ramp radii to allow smoother merges and higher design speeds. This necessitates realigning embankments and, in some cases, building entirely new bridge structures adjacent to the existing ones. Steel or pre-stressed concrete beams are delivered in segments, lifted into place by large capacity cranes during nighttime closures to minimize disruption. Drainage upgrades are essential in the interchange's low points, where stormwater can collect rapidly. New catch basins, reinforced concrete pipe, and outfall structures are installed to handle runoff from both pavement and bridge decks. Erosion control measures, such as rock riprap and vegetated swales, are placed to stabilize embankments during and after construction. The project also modernizes the roadway surface itself. Existing asphalt pavement is milled away, base layers are inspected and repaired, and new lifts of high-performance asphalt or Portland cement concrete are laid down. The surface mixes are selected for durability under heavy truck traffic and resistance to freeze-thaw cycles common in northern Nevada winters. Signage, lighting, and safety barriers are also overhauled. Overhead sign structures are erected with improved sight distances, LED lighting is added for better nighttime visibility, and new concrete barrier walls are installed to meet current impact standards. Intelligent transportation system components, traffic sensors, cameras, and variable message signs are integrated to provide real-time traffic data and incident response capability. When complete, the Reno Spaghetti Bowl project will replace a decades-old interchange with a modern, higher-capacity system built to current engineering standards, improving not just traffic flow, but also safety, stormwater control, and long-term structural resilience. Well before. The United Artists Building renovation in downtown Detroit is one of the city's most detailed historic restoration projects, turning a long-vacant skyscraper into a modern, mixed-use residential and retail property while preserving its 1920s architecture. Located on Bagley Street, just off Grand Circus Park, the building originally opened in 1928 as an 18-story office and theatre complex designed by C. Howard Crane, the same architect behind many of Detroit's classic movie palaces. For decades, it stood empty and deteriorating, but the current redevelopment is bringing it back as the residences at the United Artists Building. The restoration process began with extensive structural stabilization. Years of exposure and neglect had damaged parts of the steel frame and concrete slabs, so engineers first reinforced key load-bearing members and replaced corroded sections. The exterior limestone and brick facade required careful cleaning and patching to remove decades of grime and weathering. Damaged ornamental features were either restored in place or recast using molds based on original designs. New mortar was color-matched to blend with the historic masonry. and missing terracotta details were replicated using modern materials that preserved the look while improving durability. The interior work involved a full gut renovation. All mechanical, electrical, and plumbing systems were removed and replaced with modern infrastructure that meets current building codes. The original floor plates were reconfigured to create more than 100 residential units, with layouts designed around the existing structural grid. Crews installed new insulation, fireproofing, and acoustic barriers to bring the building up to modern performance standards while keeping as much of the historic framework visible as possible. Because of the building's age and landmark status, the renovation follows guidelines set by both the National Park Service and the State Historic Preservation Office. This means every change to the exterior or visible interior spaces must maintain the original appearance where feasible. Window openings, for example, have been restored to their historic dimensions with new energy-efficient replicas of the original steel frames. The main entrance and lobby have been rebuilt to match archival photographs with decorative plaster, marble flooring, and lighting fixtures fabricated to match the 1920s design. The old theatre portion of the complex, which once seated thousands of moviegoers, presented a different kind of challenge. Its roof and interior finishes had decayed beyond repair, so it's being stabilized rather than fully restored, with plans for potential future use as an event or retail space. Structural engineers reinforced the existing trusses and exterior walls to ensure long-term stability while keeping the theatre's shell intact. Throughout the renovation, one of the biggest challenges has been coordinating construction within the narrow footprint of downtown streets. Material deliveries are scheduled during off hours, and interior demolition debris was removed using a controlled chute system to minimize disruption. Elevator shafts were rebuilt to accommodate new cabs and fire-rated enclosures, while mechanical systems were routed through vertical chases that didn't exist in the original design, requiring careful coordination between trades. The completed building will combine ground floor retail with upper-level apartments and amenities such as fitness areas, lounges, and rooftop spaces overlooking the city. Modern safety systems, sprinklers, alarms, and pressurized stairwells have been integrated discreetly to preserve the building's character. Down on the shores of the Red Sea, where the old port city of Jeddah stretches out between desert and water, two enormous projects are quietly redrawing the map: Jeddah Central and Jeddah Economic City. Together, they represent a vision of transformation unlike anything the city has seen before, turning this historic gateway into a modern global hub for business, culture, and tourism. What makes these developments remarkable isn't just their scale, but the way they weave old and new, ambition and heritage, into something that feels distinctly Saudi, yet unmistakably international. Jeddah Central sits right in the heart of the city, taking over more than 5 square kilometers of waterfront that once housed the old desalination plant and underused industrial land. It's being reinvented as a new downtown, built around a sweeping marina and a waterfront district lined with cultural landmarks, residential towers, and entertainment spaces. The master plan revolves around 4 main landmarks: a sports stadium, an oceanarium, an opera house, and a museum, all designed to anchor Jeddah's identity as a cultural and leisure destination. Around them will rise luxury hotels, office towers, parks, and promenades, all connected by shaded walkways and open public spaces, meant to bring life back to the seafront. But this isn't just about aesthetics. The project's layout is designed around sustainability and smart urbanism, integrating renewable energy, green transport systems, and water recycling technologies suited to the coastal climate. It's a major shift for Jeddah, which has long struggled with congestion and uneven urban growth. The plan envisions a livable, walkable downtown that balances modernity with comfort, turning the Red Sea coast into a showcase for the new Saudi lifestyle that's emerging under the country's Vision 2030 framework. The idea is to create not just buildings, but experiences. places where art, commerce, and everyday life blend seamlessly. A short distance to the north, Jeddah Economic City takes that ambition and scales it up to a global level. This is the site of the Jeddah Tower, the skyscraper that aims to surpass 1 kilometer in height and become the tallest building in the world. The tower is the centerpiece of a vast mixed-use development covering more than 50 square kilometers, designed to serve as a new economic hub for trade, finance, and innovation. When complete, Jeddah Economic City will have residential neighborhoods, educational institutions, business districts, and green open spaces all linked together by advanced infrastructure and digital systems. The city's design places a strong focus on integration with the wider region. Ports, highways, and logistics corridors will tie it directly into the national network that connects Jeddah to Makkah, Medina, and eventually NEOM, farther north. In many ways, Jeddah Economic City represents the country's broader push to diversify its economy beyond oil, creating new industries that can attract global investment and talent. Taken together, Jeddah Central and Jeddah Economic City show two faces of Saudi Arabia's urban transformation. One is cultural and civic, centered on lifestyle and heritage. The other is economic and technological, reaching for the future through engineering and ambition. Both are shaping a new identity for Jeddah, a city that once served as the gateway for pilgrims, now evolving into a gateway for ideas, enterprise, and modern urban life along the edge of the Red Sea. Restoration efforts on the Colorado Big-Thompson project have involved a multi-decade sequence of upgrades, structural reinforcements, and modernization of both above-ground and subterranean components across a vast regional network. Spanning trans-mountain diversion tunnels, hydropower facilities, pumping plants, canals, reservoirs, and dam structures, the complexity of renovating this mid-20th century water infrastructure lies not only in the scale of its components, but in the critical, continuous water delivery it must maintain throughout every construction and retrofit phase. At the core of the project is the Alva B. Adams Tunnel, which transports water beneath the Continental Divide. The original tunnel lining, constructed from cast-in-place concrete following drill and blast excavation, has faced decades of hydrostatic pressure, abrasive sediment flow, and thermal expansion stress. Modern inspection robots, equipped with LiDAR and ultrasonic probes, traverse the interior to map defects. Where cracking, voids, or liner degradation is identified, hydrodemolition methods strip the compromised material. Layers of fiber-reinforced shotcrete are then applied, sometimes with embedded stainless mesh or steel lattice reinforcement, to restore structural strength and flow profile. Major valve chambers and penstocks connecting to the hydropower stations have also seen extensive retrofitting. Aging butterfly and cone valves, once manually operated and fabricated from cast iron, are being replaced with stainless steel equivalents that feature automated controls integrated into SCADA systems. Valve replacement requires dewatering and confined space access, necessitating bypass piping and upstream cofferdam installation. In some sites, penstock joints are strengthened with carbon fiber wraps and anchored against slope instability through the use of ground anchors drilled into bedrock. Reservoir and dam structures have undergone re-evaluation to comply with contemporary safety standards, especially in the context of seismic vulnerability and climate-induced hydrological extremes. Earth-filled dams, such as those at Carter Lake and Horsetooth Reservoir, have been subject to slope stability assessments using modern finite element analysis. Remediation includes flattening embankment slopes, adding chimney drains constructed with well-graded filter sands, and recompacting fill zones to increase seismic resilience. Some dam crests have been raised by several feet to increase freeboard, while auxiliary spillways are being constructed with concrete chute structures lined with energy-dissipating blocks to handle probable maximum flood events. Instrumentation throughout the system has transitioned from analog to digital. Remote monitoring nodes, including piezometers, extensometers, and pressure transducers, feed real-time data into a centralized operations center. This allows for predictive maintenance, dynamic reservoir management, and early warning during extreme weather events. Redundant telemetry paths ensure system integrity even during partial outages. The canal network and siphons responsible for water delivery to Eastern Plains users also required attention. Siphons built from riveted steel pipe were either relined with cured-in-place polymer systems or entirely replaced using slip lining techniques. Open canals were reshaped with laser grading and then lined with concrete or synthetic geomembrane to reduce infiltration losses and improve flow velocity. Turnouts and flow control gates were fitted with actuators and sensors, reducing labor demands and improving response time during flow adjustments. Throughout the renovation, work was heavily constrained by seasonal water demand and the operational requirement to maintain delivery. Construction windows were short, often confined to late fall and winter when irrigation demand was lowest. Shutdowns were planned months in advance and executed with minute-by-minute coordination between contractors and operations personnel. In many cases, redundant systems or emergency bypasses were fabricated in advance to allow full system function while isolated sections were taken offline. It began as a symbol of architectural ambition and multimodal integration. The Michigan Central Station in Detroit was originally conceived not just as a terminal, but as an infrastructure centerpiece that fused classical design with early 20th century rail logistics. Constructed beginning in 1910 and completed by 1913, the building rose from reinforced concrete foundations with structural steel framing, clad in limestone and brick masonry. Its Beaux-Arts facade, framed by Corinthian columns and ornamental cornices, concealed an internal structure engineered to support heavy dynamic loads associated with constant passenger traffic, mechanical systems, and vertical elevator shafts that once serviced the upper floors. The station's main concourse featured a vaulted ceiling with Guastavino tile archwork supported by large span steel girders, designed to accommodate both vertical thrust and lateral sway caused by thermal expansion. The train shed, located behind the main terminal, consisted of steel trusses resting on load-distributing concrete piers. These trusses were calculated to handle not only the weight of the shed itself, but also the vibration and impact loading from multiple locomotives and railcars, operating simultaneously across several parallel tracks. Drainage systems beneath the platforms collected stormwater and redirected it to below-grade retention vaults, an early example of urban runoff management. When it entered service, the station's integration with the Michigan Central Railway meant that both freight and passenger traffic could converge seamlessly, requiring the embedding of mechanical interlockings, signal rooms, and baggage routing corridors beneath the main lobby. The building's vertical tower, reaching over 200 feet, housed office floors originally intended for rail administration and later leased to a variety of commercial tenants. These upper floors were framed with cast-in-place concrete slabs supported by riveted steel beams and girders, fireproofed with terracotta tile encasements. As rail use declined in the mid to late 20th century, the structure deteriorated rapidly. Structural integrity assessments conducted in later decades revealed extensive water intrusion, freeze-thaw damage to masonry, and corrosion of steel members, particularly in the floor assemblies and roof truss systems. Restoration efforts required a sequential approach, beginning with structural stabilization. This involved shoring up weakened beams, replacing spalled concrete, and reinforcing the floor diaphragms with steel plates and epoxy-bonded carbon fiber where appropriate. Interior restoration was no less complex. Historical preservation teams catalogued and removed original architectural features, marble panels, plaster reliefs, ornamental ironwork, for off-site restoration. Meanwhile, MEP engineers designed entirely new utility systems to be discreetly integrated behind historic walls and under floor spaces, including chilled water HVAC systems, high-efficiency LED lighting arrays, and digitally controlled fire suppression and alarm infrastructure. These had to comply with modern building codes without disrupting the station's preserved aesthetic. Elevators and stairwells were either restored or replaced, and new vertical access cores were cut through abandoned service shafts, requiring careful structural reinforcement to avoid compromising existing load paths. Additionally, accessibility upgrades included ramps, widened entrances, and elevator service extending to all public floors, all designed to meet ADA standards while blending with the original design. On a site with existing grid interconnections, the Reed-Gardner Battery Energy Storage System is designed to operate as a high-capacity, utility-scale installation capable of storing and dispatching electricity with rapid response times. The project began with site preparation that accounted for both structural loading and environmental considerations. Grading crews leveled the area to accommodate containerized battery units, access lanes for maintenance vehicles, and dedicated transformer and inverter pads. The subsurface was compacted and, where necessary, reinforced with aggregate base to provide a stable platform for heavy equipment placement. The storage system uses modular enclosures, often in the form of prefabricated steel containers that house the battery cells, thermal management equipment, and control electronics. Each container sits on a reinforced concrete pad equipped with embedded conduits for both power and data connections. The battery chemistry, typically lithium-ion for this type of project, is arranged in racks with integrated battery management systems to monitor voltage, temperature, and state of charge for each module. Thermal control is a critical engineering component. Given Nevada's high summer temperatures, each container includes dedicated HVAC units and ventilation systems to keep the batteries within optimal operating ranges, preventing thermal runaway and prolonging service life. These systems are sized for redundancy, ensuring that a single failure does not compromise the integrity of the battery bank. Power conversion is handled by utility-scale inverters positioned adjacent to the battery units. These inverters transform the direct current from the batteries into alternating current synchronized with the grid. Step-up transformers then raise the voltage to match the transmission network, and protective relays and switchgear safeguard the system against faults or abnormal operating conditions. Integration with the existing substation infrastructure at the Reed-Gardner site required precise electrical engineering. Relay coordination studies, short-circuit analyses, and load flow modeling ensured that the battery system could seamlessly charge during periods of low demand and discharge during peak demand without destabilizing the grid. Control systems provide automated dispatch based on real-time conditions, with the capability for remote operation by the utility's Energy Management Center. Safety considerations shaped much of the design. Fire detection and suppression systems were installed within each enclosure, along with gas detection sensors and emergency shutoff mechanisms. Clear access routes and separation distances between units reduce the risk of fire propagation. When commissioned, the Reed-Gardner Battery Energy Storage System became a strategically located asset, capable of smoothing renewable generation variability, providing frequency regulation, and supporting grid reliability during demand spikes, all built on a foundation engineered for durability, safety, and long-term performance in a challenging desert climate. Stretching across thousands of acres in Story County, the Fort Street rebuild and the Lux Wall factory development represent two very different kinds of construction happening in the Detroit area. One focused on critical urban infrastructure and the other on high-tech manufacturing, but both show how engineering work is shaping the city's next phase of growth. The Fort Street project runs through one of Detroit's oldest industrial corridors, linking the downtown core to the southwest side and the Ambassador Bridge. It's a major reconstruction of both the roadway and the underground systems that support it. Much of the infrastructure along this route dates back decades, so the rebuild involves replacing everything from sewer and water lines to traffic signals and utility conduits. The Michigan Department of Transportation has divided the work into several segments to keep traffic moving while reconstruction continues. The first step in the Fort Street rebuild has been excavation and utility replacement. Crews dig down several feet to remove the old concrete base and install new drainage structures. followed by reinforced concrete pipe systems to handle stormwater. Electrical ducts and fiber optic conduits are placed in separate trenches to keep them accessible for maintenance. After utilities are set, a new subbase is compacted using layers of crushed stone and sand to stabilize the soil before concrete paving begins. The new pavement design typically includes a 10-inch thick concrete surface reinforced with steel dowels to handle heavy truck traffic from the port and industrial areas nearby. Because Fort Street carries a large amount of freight traffic, staging is one of the most important parts of the plan. Construction is done in sections, keeping one side of the street open while the other is being rebuilt. Temporary detours and crossovers are installed at intersections, and crews often work overnight to pour concrete and finish sections before rush hours. The new roadway design also includes modern signal systems, LED lighting, and improved pedestrian crossings. Once the underground work and paving are complete, landscaping and curbs are added to tie the rebuilt corridor back into the surrounding neighborhoods. A few miles away, in Ypsilanti Township, Luxwall is building a new factory dedicated to producing advanced, energy-efficient glass. The plant is designed to manufacture vacuum-insulated glazing, which is glass that uses a thin vacuum layer between two panes to drastically reduce heat transfer. This type of glazing has the potential to replace standard double-pane glass in buildings by offering better insulation with less material thickness. The Luxwall facility itself is a large-span industrial building built with structural steel framing, insulated wall panels, and a high-clearance roof system to accommodate production lines and lifting equipment. The floor is a continuous concrete slab designed to support heavy manufacturing machinery and precision assembly stations. Inside the plant, production areas are divided into sections for glass cutting, coating, vacuum sealing, and quality testing, all of which require clean and controlled conditions. Construction of the factory started with soil stabilization and the installation of underground utilities for processed water, compressed air, and electrical distribution. Prefabricated steel members were assembled on site using bolted connections, and once the structural frame was complete, insulated wall and roof panels were installed to close in the building. Mechanical systems for ventilation, air filtration, and temperature control were added next, as the glass manufacturing process is sensitive to dust and humidity. If you've ever traveled through Britain by train, you know the experience can be both scenic and slow, with Victorian-era infrastructure still carrying millions of passengers every day. That's exactly what the HS2 project set out to change, a high-speed rail line designed to reshape how the country moves, connecting London with the Midlands and the North at speeds the UK has never seen before. It was imagined as the backbone of a new, modern transport network, one that could rival continental Europe's fast and efficient trains while easing the pressure on the country's crowded existing lines. High Speed 2, or HS2, is being built in stages. The first phase stretches from London to Birmingham, cutting travel times almost in half. The second was originally meant to continue north toward Manchester and Leeds, linking major cities with sleek new trains running at over 320 kilometers per hour. The ambition wasn't just about shaving minutes off journeys, it was about balancing Britain's economic geography, pulling growth and investment away from the capital and spreading it toward regions that had long been left behind. In theory, faster travel meant stronger regional economies, easier business connections, and new job opportunities across the country. But building HS2 has been anything but straightforward. It's one of the largest infrastructure projects in Europe, involving hundreds of kilometers of tunnels, viaducts, and embankments carved through some of England's most densely populated areas. The sheer complexity of the route required boring machines to tunnel under London suburbs, elevating tracks across countryside landscapes, and even designing specially built wildlife bridges to protect local ecosystems. Every section of the project is a microcosm of engineering challenges: soft clay, urban congestion, ancient infrastructure, and a constant balancing act between speed, safety, and sustainability. The construction workforce alone numbers in the tens of thousands, operating across dozens of sites at once. Giant tunnel boring machines, each named and tracked like ships, have been chewing their way through chalk and clay beneath the Chiltern Hills, creating vast underground passageways for the new line. Elsewhere, massive viaducts rise over river valleys, and new depots and stations take shape in cities that have been waiting decades for this kind of modernisation. Euston and Old Oak Common in London are being transformed into vast transport hubs, designed not just for HS2, but to connect seamlessly with existing networks, integrating the old with the new. However, despite its technical brilliance, HS2 has faced intense criticism and political turmoil. Costs have soared far beyond initial estimates, delays have stacked up, and parts of the northern extensions have been scaled back or cancelled entirely, leading many to question whether the project can still deliver on its original promises. Environmental groups have voiced concerns about the loss of woodland and natural habitats, while others argue that the benefits to the broader economy still justify the disruption. Even so, what remains of HS2 still represents a massive leap forward for Britain's rail system. When the first trains begin running between London and Birmingham, they'll mark the country's entry into true high-speed travel, a mode that much of the world has already embraced. And while the vision may have shrunk from its earliest days, the project still stands as a symbol of long-term ambition, the kind of investment that tries to build not just for today's commuters, but for generations yet to come. Before a single piece of steel was erected or concrete poured, the Denver International Airport's Great Hall and concourse expansion demanded a massive logistical rethinking of how to conduct large-scale construction within one of the busiest aviation hubs in the United States without disrupting daily operations. This project focused both on increasing passenger capacity and modernizing terminal facilities, began with an intense pre-construction phase involving phased scheduling, night shift execution, and dust control protocols to minimize interference with live airport activities. Safety planning was paramount, requiring clearly demarcated work zones, continuous coordination with TSA and airport authorities, and strict adherence to Federal Aviation Administration guidelines. The first visible transformation came in the Great Hall, which lies directly beneath the iconic tented roof structure of the main terminal. Here, crews began by deconstructing outdated ticketing counters and relocating mechanical, electrical, and plumbing systems buried deep within the existing infrastructure. These systems had to remain partially operational during upgrades, requiring temporary bypasses and auxiliary equipment to handle airflow, power distribution, and fire suppression. Massive scaffolding systems were erected to allow overhead work, including structural steel reinforcements and the installation of new HVAC ducting, lighting grids, and advanced digital signage, all while maintaining public access routes through the terminal. To create more open and secure spaces, reinforced concrete walls were removed and replaced with structural steel moment frames, enabling larger, column-free zones that could accommodate modern check-in kiosks and automated baggage handling systems. Prefabricated modules were employed to reduce on-site labor time, including restroom pods, wall panels, and ceiling cassettes. This modular strategy helped reduce exposure to unforeseen field conditions and improved consistency across new construction zones. The concourse expansion occurred simultaneously on multiple piers, each requiring different approaches depending on existing infrastructure and passenger volume. On the west side, crews extended the A and B concourses with new gate areas constructed on deep pile foundations. These foundations were drilled to depths exceeding 50 feet and filled with high-strength concrete to ensure stability against expansive clay soils prevalent in the Denver area. Above ground, a steel superstructure supported wide-span roof trusses and curtain wall assemblies made from high-performance glazing designed for energy efficiency and glare reduction. Mechanical penthouses were added atop the new wings to house air handling units and electrical transformers, feeding state-of-the-art building systems that are integrated into a centralized control platform for maintenance efficiency. The new gates were designed with dual jet bridge capability, allowing for faster turnaround times and more flexible aircraft servicing. Interior finishes were chosen for durability and ease of maintenance, including terrazzo flooring, antimicrobial surfaces, and acoustically treated ceiling panels to mitigate noise in passenger waiting areas. Throughout both the Great Hall and Concourse projects, sustainability measures were embedded into construction practices. Construction waste was diverted through recycling programs, while water-efficient fixtures, daylight-responsive lighting, and energy recovery ventilation were incorporated into the design to reduce long-term operational loads. The project also embraced digital twin technology, allowing engineers to simulate performance outcomes and track asset conditions in real time post-construction. The few civil engineering efforts in North America rival the logistical scale and environmental complexity of the Soo Locks expansion project in Sault Ste. Marie, Michigan. At the heart of this endeavor lies the construction of a new, modern lock chamber to replace the aging and underutilized Davis and Sabin locks, making way for a structure capable of accommodating the largest Great Lakes freighters, vessels over 1,000 feet long and carrying over 70,000 tons of iron ore per trip. Planning for this megaproject required extensive geotechnical investigation, structural design coordination, hydraulic modeling, and phased construction that could integrate with ongoing lock operations and preserve commercial navigation throughout the build. The initial step involved dewatering a large section of the existing canal where the new lock would be constructed. This required the installation of steel sheet pile cofferdams driven deep into bedrock, reinforced with cross-bracing and anchored to resist the immense hydrostatic pressure of the St. Mary's River. Once the cofferdams were sealed and dewatering pumps reduced the water table, excavation of glacial till, cobble, and fractured bedrock began. Controlled blasting was necessary to remove heavily jointed bedrock layers, and each detonation was carefully monitored to avoid damaging adjacent structures or disrupting vessel traffic in the nearby Poe and MacArthur locks. As excavation reached design depth, foundation preparation involved smoothing and cleaning the bedrock surface, followed by the placement of mass concrete footings and pile caps. High-strength concrete with low permeability characteristics was used to ensure durability in this highly saturated freeze-thaw environment. Reinforcing steel cages, prefabricated and lowered into place using tower cranes, formed the basis of massive vertical lock walls. Each section was cast using slip-form techniques, allowing continuous concrete pours to maintain quality and avoid cold joints. Embedded within the lock walls were corrosion-resistant mechanical systems, including gate recesses, pintle bearings, and hydraulic conduits. The lock gates themselves represent a significant engineering milestone. Designed as mitre gates with steel skin plates and internal trusses, they are fabricated off-site and floated into place via barge, then lowered into sockets, machined into the concrete floor. Each gate weighs several hundred tons and must align precisely to ensure a watertight seal. Adjacent to the gates, culvert valve chambers and culvert galleries were constructed to control the massive volumes of water used to fill and empty the lock chamber. These culverts, embedded within the lock's concrete walls and floor, operate using gravity-fed systems regulated by bulkhead slots and hydraulically actuated valves, optimized for smooth water transitions to minimize turbulence. Maintaining construction access in such a confined and operationally sensitive area demanded a high degree of sequencing. Staging areas were created along both riverbanks, with temporary trestles and barge-mounted cranes deployed for material handling. All construction activities had to comply with stringent environmental regulations, including sediment control, aquatic habitat protection, and water quality monitoring. Ice control systems were integrated into the final design, including bubbler lines and heating elements to prevent freezing in critical mechanical assemblies during winter operations. Waters of Lake Mead, the construction of intake number 3 unfolded as a feat of deep water and tunneling engineering designed to secure southern Nevada's water supply even under conditions of severe drought. The project began with precise geotechnical surveys, both above and below the lake surface, to determine the optimal location for a new intake point at a lower elevation than the two existing ones. This position ensured the system could continue drawing water even if the lake level dropped dramatically. Work commenced with the creation of a submerged intake structure positioned hundreds of feet below the water surface. Divers and remotely operated vehicles assisted in the placement of this massive reinforced concrete assembly, which included a steel intake dome and trash racks to prevent debris from entering the system. Fabrication occurred onshore in modular sections, which were then floated into position and carefully lowered using marine cranes and barges equipped with winch systems. Simultaneously, crews on land began excavation of a deep access shaft on the shoreline. This vertical shaft extended down through layers of volcanic rock and sediment, eventually connecting with the horizontal tunnel that would link the shore facilities to the intake structure. Tunnel boring machines, designed for hard rock excavation, advanced slowly beneath the lake bed, maintaining constant pressurization to prevent water ingress. Spoil from the tunneling operation was hoisted up the shaft, while continuous ground monitoring ensured stability and alignment. The tunnel lining consisted of precast concrete segments assembled in place behind the tunneling shield to create a watertight passage. Each segment was fitted with gaskets and sealed to withstand the hydrostatic pressure from the overlying lake. As the boring progressed toward the submerged intake, alignment tolerances were kept within inches, ensuring a precise final connection. Once the tunnel and intake were joined, engineers completed the installation of stainless steel piping, control valves, and flow regulation equipment. The system was integrated into the existing water delivery infrastructure, with pumping capacity designed to handle the peak demands of the Las Vegas Valley. Safety systems, including isolation gates and inspection access points, were incorporated to allow future maintenance without interrupting water service. The COSM and development at Cadillac Square project is one of the central pieces of Detroit's downtown redevelopment plan, sitting right next to Campus Martius Park and a short walk from the Hudson Site. It's a mixed-use district being built on what was once a series of parking lots, turning that open space into a dense block of offices, retail, entertainment, and public gathering areas. The project is led by Bedrock, the same developer behind Hudson's, and it's meant to create a continuous corridor of activity running through the center of the city. The centerpiece of the development is the COSM Entertainment Venue, a specialized immersive dome designed for large-scale visual experiences like sports, concerts, and cinematic events. It's based on LED dome projection technology that wraps the viewer in a 360-degree image field. The structure itself is a reinforced steel frame with a curved truss system that supports the dome panels and projection surface. Every section of the dome has to meet tight tolerances for alignment, so the imagery remains seamless. The venue will also include hospitality areas, food service, and event spaces built into the lower levels. Surrounding the COSM site, the Cadillac Square development adds several mid-rise buildings that blend commercial, office, and residential functions. These structures range from roughly 8 to 12 stories, using a combination of reinforced concrete and structural steel. The design follows a modern pattern that still matches the historic street grid, with ground floors set up for retail and restaurants, while upper floors are dedicated to apartments and workspaces. The facades are being built with a mix of glass, metal, and masonry, intended to fit in visually with Detroit's older architecture. The foundation work across the Cadillac Square site has involved deep utility relocation because of the amount of infrastructure already buried beneath that area. Crews had to reroute water, electrical, and communication lines before excavation could begin. Once that was complete, Pile driving and drilled shafts were used to establish the foundation supports, especially under the COSM dome, where the load from the structure's curved frame is concentrated on specific points rather than distributed evenly. Construction sequencing has been coordinated tightly with surrounding projects to avoid gridlock downtown. Deliveries move through controlled access routes, and cranes are placed carefully to minimize interference with adjacent buildings and public walkways. The site also borders several active streets, so temporary decking and barriers have been used to maintain pedestrian access while work continues. From an engineering standpoint, the COSM structure is the most technically demanding part of the project. The dome's geometry requires precise fabrication, and the integration of audio-visual and climate systems inside the structure has to be planned before final assembly, because retrofitting is nearly impossible once the panels are sealed. Each dome panel includes mounts for LED arrays and acoustic insulation, which are installed in controlled conditions before being lifted into place. When the Cadillac Square development is complete, it will add several 100,000 square feet of usable space to downtown Detroit and create one of the most active public zones in the city's core. Between the COSM Dome, the retail spaces, and the new residential towers, the project combines structural complexity with dense urban planning, continuing Detroit's shift from surface parking to a modern, mixed-use downtown. In the quiet countryside of southern France, surrounded by pine forests and rolling hills, there's a construction site unlike any other on Earth. It's not another dam or bridge or skyscraper. It's a machine built to recreate the power of the sun. This is ITER, the International Thermonuclear Experimental Reactor, and it represents one of the most ambitious scientific collaborations in human history. The goal here is nothing short of mastering nuclear fusion, the same reaction that fuels stars, and turning it into a practical source of energy for our planet. The concept sounds simple in theory, but has pushed the limits of engineering for decades. Fusion happens when two light atomic nuclei, usually forms of hydrogen called deuterium and tritium, collide at extremely high temperatures and fuse into helium, releasing enormous amounts of energy. The problem is that replicating those conditions on Earth means creating and controlling plasma that's hotter than the core of the sun, about 150 million degrees Celsius, and keeping it stable long enough to extract useful power from it. That's where ITER comes in. At the heart of the project is the tokamak, a donut-shaped reactor designed to contain the plasma using magnetic fields so powerful they could lift aircraft carriers. The machine itself is a masterpiece of precision. Its vacuum vessel weighs over 5,000 tons. Its superconducting magnets are cooled to near absolute zero, and every component must align with millimeter accuracy, despite being the size of a small building. The idea is that when the system is fully operational, the reactor will produce 10 times more energy than it consumes, something no fusion experiment has ever achieved before. What makes ITER truly remarkable is how global it is. It's being built through a partnership of 35 nations, including the European Union, China, the United States, Russia, Japan, India, and South Korea. Each partner contributes different components, from cryogenic systems to magnet coils to diagnostic sensors, and all of them have to fit together perfectly when assembled in France. Coordinating that kind of international supply chain is an engineering feat in itself, with massive pieces of hardware shipped across oceans and transported by custom-built convoys that crawl through rural roads to reach the site. The scale of the infrastructure around the tokamak is equally astonishing. There's a massive cryoplant to cool the magnets, a system of vacuum pumps, cooling water loops, radio frequency heating systems, and an entire electrical network dedicated to feeding the experiment's colossal appetite for power. When ITER begins its first plasma runs, it will consume more electricity than a medium-sized city, though the aim is to prove that fusion can eventually produce far more energy than it uses. Yet the challenge isn't just technical, it's also philosophical. Fusion has been called the energy of the future for over half a century, and ITER's success or failure could finally determine whether that future is real. If it works, it could open the door to commercial reactors that generate clean, virtually limitless energy from seawater, with no carbon emissions and almost no radioactive waste. But for now, ITER remains an experiment, a monument to human cooperation and scientific persistence, standing quietly in Provence as thousands of engineers and scientists work to capture the power of the stars here on Earth. It began as a bold vision to create a state-of-the-art multi-sport facility in northern Colorado, materialized in Windsor through the phased construction of the Future Legends complex. This expansive development required not only precise engineering, but also meticulous land planning and infrastructure coordination to accommodate a mix of professional-grade athletic fields, event venues, lodging, and commercial amenities spread across several dozen acres. Grading and site development were among the first large-scale efforts. Given the varied topography of the selected parcel, mass earthwork was undertaken to create a balanced cut-and-fill profile, minimizing the need for imported or exported soil. GPS-guided bulldozers and scrapers reshaped the terrain to accommodate field layouts with accurate drainage grades, ensuring surface runoff would be directed away from play surfaces and spectator areas. Subsurface utilities were installed in tandem, including pressurized irrigation systems, storm drains, and fiber optic communication lines. Central to the complex is a professional stadium featuring a full synthetic turf field engineered for both baseball and soccer configurations. This required a multi-layered subgrade construction, beginning with a geotextile separator, followed by a stone drainage blanket and permeable base aggregate. Embedded within this system is a network of perforated drainage pipes connected to sump basins that prevent water accumulation during heavy rains. The turf system itself includes shock pads for impact attenuation and is anchored with inlaid seams and edge restraints to resist displacement during play. Surrounding the stadium are multiple regulation-size baseball diamonds and multi-use soccer fields. These grass fields required installation of precision laser-graded sand-capped root zones to support Kentucky bluegrass sod, chosen for its wear tolerance and climatic adaptability. Each field is served by a dedicated irrigation zone controlled through a centralized, weather-responsive smart controller. Dugouts, backstops, and netting systems were prefabricated off-site and crane set into place to expedite field completion. Beyond the playing surfaces, a high priority was placed on vertical construction, including indoor training facilities, locker rooms, team offices, and hospitality areas. These structures were framed with a mix of structural steel and tilt-up concrete panels. Steel framing allowed for large clear spans in gymnasiums and indoor turf spaces, while tilt-up panels provided rapid erection and thermal mass benefits. Mechanical systems were integrated with high-efficiency rooftop units, and all lighting was based on LED arrays with daylight harvesting sensors in office zones. To support year-round operation and events, additional infrastructure was implemented. Parking lots were built with reinforced subbuses and pervious asphalt sections in select areas to manage stormwater on site. Utility service yards and maintenance facilities were placed at the perimeter for discrete accessibility, while pedestrian pathways used stamped concrete and bollard lighting to guide foot traffic safely between venues. Construction phasing was essential due to weather constraints and funding schedules. Each component was sequenced to ensure utility readiness and site access without disrupting adjacent ongoing construction. This required close coordination between general contractors, specialty subcontractors, and local jurisdiction inspectors to maintain timeline integrity and safety compliance. From an engineering standpoint, Detroit Metropolitan Wayne County Airport is a layered composition of airfield systems, structural innovations, and transportation logistics brought together under one of the busiest aviation hubs in the Midwest. Its design and continual upgrades illustrate the demands of modern air travel on both infrastructure and operations, particularly in a four-season climate that presents snow, wind shear, and high summer heat. The layout of the airfield is dictated by a network of parallel and intersecting runways, each surfaced with high-strength Portland cement concrete capable of supporting repeated impact loads from wide-body aircraft. These runways are underlain with aggregate-based courses and treated subgrades to mitigate frost heave and subsurface water migration. Embedded within each runway and taxiway are systems for runway lighting, electrical cable ducts, and aircraft guidance signs. Engineers incorporated FAA standard grooving on runway surfaces to improve water drainage and reduce hydroplaning risk, a critical detail in airport pavement construction. The terminals themselves are multi-story steel and concrete structures anchored by deep pile foundations. These piles extend below the frost line and into stable soil strata, designed to distribute vertical loads from the concourses and jet bridges. Each terminal is framed using steel columns and wide flange beams with composite concrete floor decks, chosen for their high strength-to-weight ratio and ability to span large open areas like ticketing halls and baggage claim areas. The roofs are framed with long-span steel trusses that allow for open, column-free spaces in the concourse areas, maximizing circulation and passenger flow. The McNamara Terminal, one of the key expansions at the airport, features an automated people mover system running the length of its concourse. The guideway was constructed with precast concrete guide beams mounted on cast-in-place piers, incorporating seismic joints and expansion bearings to accommodate thermal movement and vibration. The vehicles operate on a cable pull system embedded within the guideway, with control systems synchronized to station gates to optimize dwell times and passenger throughput. Beneath the passenger terminals lie extensive baggage handling systems, high-speed conveyors, diverters, and scanning units routed through multiple levels and security checkpoints. Mechanical engineers coordinated ductwork, fire suppression piping, and electrical conduit to share tight overhead spaces with baggage infrastructure, requiring three-dimensional coordination models and clash detection software during the design phase. Airside operations are supported by a fleet of underground utilities, including jet fuel hydrant systems, aircraft ground power units, and preconditioned air supply points. The hydrant fueling system was built with double-walled underground piping and leak detection monitoring, routed through trench boxes laid beneath the tarmac and connected to fuel farm distribution pumps at a remote site. Snow removal and de-icing are another critical infrastructure component. The airport includes heated pavement zones at gate positions, glycol collection systems with detention ponds, and airfield maintenance buildings equipped with vehicle staging, snowplow maintenance bays, and bulk material storage. Drainage systems are engineered to divert and treat de-icing fluids before discharge, ensuring compliance with environmental regulations. Rolled into the desert, the planning of the Interstate 11 and Boulder City bypass demanded a precise understanding of both geography and traffic flow. The corridor cuts through a region of rugged hills and arid basins, where summer temperatures can soar above 100 degrees Fahrenheit, so designers had to consider material performance under extreme heat and long-term durability. The primary objective was to create a high-speed, limited-access highway segment that would divert heavy truck and tourist traffic away from the narrow, congestion-prone streets of Boulder City, while maintaining efficient connectivity between the Hoover Dam area and the Las Vegas Valley. Initial site work began with large-scale grading operations. Crews employed scrapers, dozers, and articulated haul trucks to carve the roadbed alignment into the natural contours, moving hundreds of thousands of cubic yards of material. In some segments, blasting was necessary to cut through solid rock outcrops, followed by rockfall mitigation measures such as wire mesh draping and retaining wall construction. The design incorporated long, gentle curves and extended site distances to meet interstate safety standards, meaning that excavation and fill had to be carefully balanced to avoid excessive hauling. Drainage posed another major engineering consideration. With infrequent but intense desert storms, the bypass required an extensive system of culverts, trapezoidal ditches, and energy dissipators to channel flash flood waters beneath the roadway without eroding embankments. Engineers designed these structures to handle peak flows far greater than typical rainfall events, ensuring resilience against rare but destructive weather. Paving operations utilized multiple lifts of asphalt concrete with a base course laid over compacted aggregate, followed by intermediate and surface courses. The surface mix was engineered to resist rutting and oxidation in high-temperature conditions, with polymer-modified binders improving flexibility. The main line was constructed with full-depth shoulders, rumble strips, and high-visibility thermoplastic striping to enhance safety. Bridges were a critical component, particularly over the El Dorado Dry Lake and other low points. These structures used precast, pre-stressed concrete girders set on cast-in-place piers and abutments, allowing rapid erection while maintaining structural capacity for heavy freight loads. Expansion joints and bearing pads were selected for durability in the large thermal swings typical of the Mojave climate. Once major earthwork and structural elements were in place, intelligent transportation systems were installed, including variable message signs, traffic monitoring sensors, and emergency pull-off areas. The completed bypass transformed regional travel, reducing congestion through Boulder City and cutting travel times toward Arizona, while providing a modern, engineered corridor built to interstate specifications for decades of service. Rising from the dense urban core, just west of the Detroit City FC Stadium, also known as Alumni 5 Field, is a purpose-built soccer venue being developed to give Detroit City FC a permanent home that matches the growth of the club and its fan base. Located within the city limits, near the old site of Detroit City's existing training grounds, the project replaces the temporary setups used in previous seasons with a fully engineered stadium designed for professional-level competition and year-round community use. The design calls for a stadium with a seating capacity in the range of 6,000 to 8,000, expandable for larger events. Structurally, the venue is being built with a mix of cast-in-place concrete for the main grandstands and structural steel framing for the upper seating decks and roof canopies. The concrete sections form the lower bowl, which is poured in stepped rises supported by reinforced retaining walls and columns. Above that, the steel structure supports prefabricated seating platforms and tensioned roof membranes designed to shelter the main stands while leaving the pitch open to natural light. The field itself is constructed to FIFA standards, with a full drainage and heating system below the playing surface. Crews excavated and layered multiple strata of material, beginning with a compacted subgrade, followed by perforated drainage pipes in gravel trenches, and then several inches of sand and engineered root zone mix. A subsurface heating network of flexible piping runs through this base, circulating warm water during cold months to keep the turf playable through Detroit's winter season. The playing surface will be a high-performance hybrid grass system, combining natural turf with synthetic reinforcement to handle heavy use without deterioration. Around the field, precast concrete retaining walls form the perimeter and support the lower seating rows. The main grandstand on the west side houses locker rooms, training spaces, offices, media facilities, and mechanical rooms underneath the stands. These back-of-house spaces are built with reinforced masonry and steel framing, designed for easy access from both the player tunnels and the exterior service drives. The east side and ends of the stadium are designed for flexibility. Modular bleacher systems can be added or removed depending on attendance, allowing the venue to adapt for both league matches and community events. The north end is planned to host the most vocal supporter section, with integrated safe standing railings and dedicated concourses. The concourse circulation paths are constructed with reinforced concrete slabs over structural steel beams, finished with slip-resistant coatings and weatherproof expansion joints. Above the main stands, the roof canopy uses lightweight steel trusses covered by PTFE fabric panels. The material allows natural light to pass through while blocking direct rain and glare, reducing both weight and maintenance compared to traditional roofing. Electrical conduits are embedded in the canopy framing to support lighting arrays, speakers, and broadcast cameras. Site work includes new parking areas, stormwater management basins, and public plazas surrounding the entrances. The stadium is connected to nearby transit corridors through pedestrian pathways, with retaining walls and ramps designed to meet ADA accessibility standards. Utilities for water, electrical, and sewer service are routed through underground conduits that also serve potential future expansions such as retail spaces or community facilities adjacent to the stadium. Alumni 5 Field's construction emphasizes modularity and efficiency. Many structural components are prefabricated off-site, including seating units, steel trusses, and canopy panels, allowing for faster assembly once foundations are in place. The project also incorporates energy-efficient lighting, low-flow plumbing fixtures, and provisions for future solar integration. In the vast emptiness of northwestern Saudi Arabia, where desert and mountains stretch endlessly under the sun, a line of glass and steel is being drawn across the landscape. A city unlike any that has ever been built before. It's called The Line, and it forms the central vision of NEOM, a futuristic megaproject meant to redefine what urban living can be in the 21st century. The idea sounds almost impossible at first, a city that isn't sprawling outward, but extending straight for hundreds of kilometers, only 200 meters wide, yet home to millions of people. But that's exactly the scale of ambition Saudi Arabia is pursuing, nothing less than the reinvention of civilization itself. The concept behind The Line begins with simplicity. Instead of spreading a city outward in all directions, it compresses everything into a single linear corridor that runs through desert valleys and over coastal plains. The two mirrored walls of the city rise more than 400 meters, enclosing a narrow interior where people will live, work, and travel vertically rather than horizontally. The structure is designed to function as a continuous vertical metropolis where everything, from housing and offices to schools, parks, and public transit, is stacked efficiently inside a climate-controlled environment. At its core, the line is meant to operate without cars, roads, or traditional streets. Instead, it relies on a high-speed underground transport system that can move people from end to end in minutes. The idea is that every daily need, groceries, healthcare, education, recreation, should be within a 5-minute walk. By eliminating cars and long commutes, the designers aim to create a city where time is reclaimed for people, where nature and urban life coexist without one overwhelming the other. Sustainability sits at the center of the entire plan. The line is being built to run entirely on renewable energy, primarily from solar and wind power, and its compact footprint minimizes land use and environmental impact. The vertical design allows the surrounding desert and mountains to remain untouched, preserving natural ecosystems while housing millions of people in a fraction of the space that a normal city would require. The structure's mirrored facade isn't just aesthetic. It reflects sunlight to reduce heat absorption and helps control the city's internal temperature. Engineering something of this magnitude pushes the boundaries of what's physically possible. The foundation requires precision construction over uneven terrain, and the structural demands of building two continuous walls hundreds of meters high across such distances are immense. The integration of transportation systems, data networks, energy grids, and vertical living spaces has to function seamlessly for the vision to work. Every part of the city will be monitored and managed through AI-driven systems, adjusting lighting, temperature, and logistics dynamically to optimize efficiency and comfort. The line also represents a broader idea about the future of Saudi Arabia. It's not just a mega project, it's a statement of national transformation. It reflects the country's drive to diversify beyond oil, to attract technology, investment, and global talent, and to present itself as a center of innovation. For the government, the line is both an economic experiment and a symbol of ambition, projecting the image of a nation willing to take risk to shape the next century. Whether it succeeds or not, the line is already changing the conversation about what cities can be. It's forcing engineers, architects, and planners around the world to imagine new forms of living, new ways of organizing society, and new relationships between humans and the environment. In the middle of the desert, a city that runs in a straight line may seem improbable, but that's precisely the point. It's a bet on imagination and on the belief that the future doesn't have to look anything like the past. Deep beneath the Continental Divide, the Eisenhower-Johnson Tunnel rehabilitation represents one of the most technically demanding infrastructure renewal efforts ever undertaken in Colorado's high-altitude environment. Built in the 1970s and 1990s respectively, the twin bores of the tunnel system have carried tens of millions of vehicles annually through the Rocky Mountains, serving as a vital east-west corridor along Interstate 70. Over time, the structure, systems, and finishes within both bores experienced wear from traffic vibration, snow, and ice control chemicals, freeze-thaw cycling, and constant exposure to vehicle emissions, necessitating a series of major upgrades to maintain safety and operational performance. The rehabilitation began with a structural inspection phase that included laser scanning, ground-penetrating radar, and core sampling to evaluate the condition of the concrete liner and surrounding rock mass. In several zones, the original shotcrete and reinforced concrete lining showed signs of delamination, cracking, or seepage, particularly near the tunnel portals, where water infiltration is most severe. These areas were carefully chipped out, cleaned, and replaced with high-performance repair mortars and corrosion-resistant rebar. In certain high-stress zones, carbon fiber reinforcement wraps were applied to enhance tensile strength without significantly reducing clearance for oversized freight loads. One of the largest challenges was replacing or upgrading the tunnel's mechanical and electrical systems without closing it entirely to traffic. Crews operated almost exclusively at night, with strict work windows limited to a few hours between full traffic flow periods. The existing ventilation system, which includes massive jet fans mounted along the tunnel crown, was upgraded with higher capacity, variable speed fans connected to new control panels and smoke detection systems. These fans are critical for exhausting vehicle emissions and providing smoke control in the event of a fire. Fire life safety upgrades also included replacing emergency lighting, upgrading fire hydrant stands, and installing thermal imaging cameras for real-time hazard monitoring. Drainage improvements were a key aspect of the work. The original subfloor drainage system, designed to carry meltwater and seepage out of the tunnel, had become partially clogged in some areas. To restore functionality, crews removed segments of the tunnel roadway to access and replace underdrains with perforated HDPE pipe encased in filter aggregate. Trench grates and catch basins were also re-engineered to better capture surface water and prevent icing hazards. These interventions were especially crucial given the extreme winter maintenance demands in this corridor. In tackling the extreme demands of spanning the Straits of Mackinac, a 5-mile wide, windswept channel where Lake Michigan and Lake Huron converge, the Mackinac Bridge project stands as a masterclass in long-span suspension bridge engineering. Designed to accommodate seismic movement, thermal expansion, gale force winds, and ice flows, the bridge required a foundation-to-finish approach that pushed the boundaries of mid-20th century civil engineering. Work began with the placement of massive caissons in the deep strait. These caissons, steel cylinders reaching down to bedrock, were sunk using a combination of pneumatic excavation and underwater blasting. Once in place, they were backfilled with tremi-concrete to form the piers that would support the suspension towers. The towers themselves rise from these caissons and were assembled using high-tolerance riveted steel plates, lifted by derrick cranes mounted on temporary platforms. Due to the depth and water conditions, the foundation work took several seasons and required round-the-clock shifts with divers, dredgers, and engineers coordinating in tight, hazardous quarters. The twin suspension towers, over 500 feet tall, consist of welded steel box sections built segmentally. Each section was hoisted using cableways strung between temporary falsework and then precisely aligned and pinned. Once both towers reached full height, the construction team began spinning the main cables, a process that involved passing individual wires back and forth across the span using a spinning wheel, then compacting and binding the bundles into the final diameter. These cables were anchored into massive concrete anchor blocks at each end of the bridge, poured over bedrock and reinforced with thousands of tons of rebar to resist the horizontal forces imposed by the suspended roadway. With the main cable secured, vertical suspender cables were hung at set intervals and tensioned to support the weight of the roadway deck. The deck itself was constructed using steel trusses and orthotropic deck panels, lifted into place from barges using floating cranes and suspended from the cables using custom fabricated clamps. Expansion joints and rocker bearings were integrated into the deck structure to accommodate longitudinal movement caused by temperature variation and traffic loads. The bridge was designed to flex several feet in any direction, a dynamic capacity necessary to endure winter ice loads and summer thermal expansion. Wind tunnel testing and aerodynamic modeling informed the bridge's profile, which includes a narrow, open-grid center lane section that reduces wind resistance and allows air to pass through the deck. Wind dampers and tuned mass dampers were also considered in the design to mitigate oscillations during high wind events. Paint systems for the structural steel involved multiple layers, including zinc-rich primers and elastomeric coatings designed to withstand harsh lake effect environments and freeze-thaw cycles. Maintenance access was engineered into the bridge with catwalks, internal tower ladders, and inspection rail trolleys integrated into the superstructure. De-icing and runoff control systems were also embedded into the deck, including scupper drains and weather monitoring sensors that inform bridge operation decisions. The Tahoe-Reno Industrial Center was developed as one of the largest industrial parks in the world, requiring infrastructure planning on a scale similar to that of an entire small city. The site's transformation began with large-scale earth moving to create graded pads capable of supporting massive distribution centers, manufacturing plants, and data facilities. The grading process had to balance cut and fill operations to minimize hauling distances, with engineered slopes and retaining structures where topography changed abruptly. Road construction formed the backbone of the development. A network of wide, heavy-duty roadways was built to accommodate high volumes of tractor-trailer traffic, with asphalt pavement designed for significant axle loads and turning stresses at intersections. The roadway system included multiple access points to Interstate 80, requiring coordinated design with state transportation agencies to meet highway safety and capacity standards. Utility infrastructure installation was carried out in parallel with site grading. Water supply lines, sanitary sewer systems, and stormwater drainage channels were laid out to serve multiple parcels while maintaining flexibility for future expansion. Electrical distribution was a critical component, as the park's intended tenants, particularly data centers, require extremely high and stable power capacities. Substations, transmission lines, and underground cabling were installed with redundancy in mind, ensuring uninterrupted service. Telecommunications infrastructure was equally important, with fiber optic networks installed throughout the park to support high-speed data transfer. Trenching for these lines was coordinated with other utility work to minimize disruptions and maintain efficient construction sequencing. Given the park's desert location, stormwater management was designed to handle sudden, high-intensity rainfall events. Detention basins, concrete-lined channels, and culvert systems were built to capture and control runoff, protecting both the rising high on the Ethiopian plateau, more than 2 kilometers above sea level. Addis Ababa has always been a city of layers, old and new, formal and informal, chaotic and alive. But over the past few years, the city has begun to take on an entirely new shape. The Addis Ababa City Corridor and Smart City Project is the centerpiece of that transformation, a sweeping plan to modernize the capital, expand its infrastructure, and create a blueprint for what a 21st century African metropolis can look like. At its heart, the project is about connection. Addis Ababa has grown rapidly, with millions of people moving in from rural regions, but the city's layout and infrastructure never quite kept pace. Roads became crowded, neighborhoods expanded without clear planning, and public services struggled to keep up. The City Corridor Plan aims to tie it all together, a network of modern boulevards, transit routes, and green corridors stretching across the city, designed to integrate housing, commerce, and technology in one continuous urban system. Think of it as both a transportation project and a digital backbone, built to link everything from the city's financial district to its emerging industrial zones. The smart city component is what makes it truly forward-looking. It's not just about widening roads or adding new buildings. It's about embedding intelligence into the fabric of the city itself. Sensor-based traffic management, integrated public data systems, and sustainable utilities that can monitor and adapt in real time. Streetlights powered by solar panels, automated waste collection, water systems that track usage and detect leaks, and transport routes that update dynamically based on congestion. All of these features form part of the vision. Addis Ababa isn't just being expanded, it's being reprogrammed. Alongside the technology, there's also a strong architectural and social vision. The new city corridors are planned to include dedicated pedestrian paths, landscaped parks, and mixed-use developments that bring homes, offices, and public spaces together. Rather than separating zones by function, the aim is to create integrated communities that reduce the need for long commutes and support more sustainable living. It's a response to the sprawl that has defined much of the city's past growth, turning what used to be dusty, disconnected suburbs into modern, connected districts. The construction itself is happening in phases, with local and international teams working together to upgrade transport corridors, build smart infrastructure, and prepare new land for development. It's a massive logistical challenge involving coordination between ministries, tech companies, and city planners, all while trying to minimize disruption in one of Africa's busiest urban centers. But despite the complexity, progress continues steadily, with visible changes appearing year by year. New roads lined with smart lighting, new districts emerging with coordinated urban layouts, and data centers forming the digital core of the city's new systems. What makes the Addis Ababa City Corridor project stand out isn't just its scale, but its symbolism. Ethiopia is positioning itself as a regional leader in technology and infrastructure, and the capital city is its proving ground. The project represents a shift from reactive urban growth to proactive, technology-driven design, an attempt to future-proof a city that's expected to keep growing for decades to come. And when it's complete, Addis Ababa could stand as one of the first truly smart cities on the African continent, built not just to handle its population, but to evolve intelligently alongside it. What makes the Gross Reservoir expansion particularly notable from an engineering standpoint is not just the increase in storage volume, but the sheer complexity involved in raising a massive concrete dam in situ, while maintaining safety, environmental compliance, and hydrologic function. The project revolves around the elevation of the existing dam structure, originally built in the 1950s, to nearly double the reservoir's capacity, thereby enhancing the long-term water reliability for the Denver metropolitan area. The core of the expansion involves adding height to the dam crest using roller-compacted concrete, a technique chosen for its rapid placement and high strength. Before this process could begin, detailed geotechnical surveys and structural assessments were conducted on the existing dam face and foundation. Crews cleaned, scarified, and roughened the old concrete surface to ensure bond integrity with the new layers. Then, a construction staging area was established below the dam, including mixing plants, conveyors, and cooling systems to support uninterrupted RCC placement. This material was delivered in massive batches and placed in lifts, each typically less than 1 foot thick, compacted with vibratory rollers before the next layer was added. One of the critical challenges was maintaining structural monolithicity across old and new concrete interfaces. Water stop systems were embedded at construction joints to prevent seepage, and grout enrichment zones were applied in transition areas to ensure full load transfer. To handle the thermal stresses that come with such a large volume of concrete, the RCC mix was designed with low cement content and placed during cooler times of day, sometimes even at night, to minimize temperature gradients and avoid cracking. Adjacent infrastructure required significant adaptation. The reservoir's spillway had to be realigned and enlarged to accommodate increased discharge capacity under extreme storm conditions. This involved the construction of a new chute and energy dissipation basin, built with high durability reinforced concrete and designed using computational fluid dynamics models to optimize flow control and prevent downstream erosion. Additionally, the intake structure, located at depth near the dam base, was retrofitted with extended vertical gates and enhanced debris exclusion systems to accommodate the new water levels and future sediment inflows. Access improvements were essential to facilitate the scale of the operation. Narrow, winding mountain roads were widened and reinforced with retaining walls, geogrid stabilized embankments, and asphalt overlays capable of supporting heavy construction traffic. Equipment staging zones were built into switchbacks, while dust suppression and runoff controls, such as sediment traps and hydro-mulching, were continuously deployed to limit ecological impact in the forested watershed. Environmental compliance was managed through a comprehensive mitigation strategy, including stream restoration projects, fish habitat enhancements downstream, and continuous turbidity monitoring in discharge channels. Construction timing was carefully coordinated with wildlife breeding seasons and precipitation patterns to minimize disruption to sensitive ecosystems. To ensure structural integrity and operational control over the long term, the project also introduced new instrumentation across the dam body and reservoir basin. This includes piezometers, joint meters, and laser scanning targets embedded within the new RCC layers and surrounding terrain. These instruments provide real-time data on stress distributions, deflection, seepage, and uplift pressures, feeding into a central monitoring platform overseen by dam safety engineers. On a site that once lay fallow and largely undeveloped, the construction of Blue Oval Battery Park marked a decisive leap into the future of high-volume electric vehicle component manufacturing. This sprawling industrial complex, designed to support the fabrication and assembly of lithium-ion battery cells and modules, demanded advanced planning and precision across every phase of construction, from grading and utilities to cleanroom commissioning. With a footprint spanning several million square feet, the facility was conceived not merely as a plant, but as a vertically integrated system with embedded energy, safety, and logistics infrastructure tailored for battery production at scale. The project began with large-scale site preparation involving the removal of unsuitable soils, installation of wick drains to accelerate consolidation, and the laying of geotextile fabric beneath engineered fill to stabilize the subgrade. Heavy compaction equipment, GPS-guided grading systems, and automated moisture control were employed to achieve stringent flatness and density tolerances across hundreds of acres. Underground utility corridors were trench cut in parallel with high-capacity storm drains, electrical conduit duct banks, and chilled water supply lines installed in tandem to minimize rework and speed up scheduling. Once the building pad was stabilized, the structural steel phase commenced. Massive steel columns, girders, and joists were prefabricated and brought to site for rapid erection using crawler cranes and aerial work platforms. The roof system, designed to support HVAC units, solar panels, and sprinkler infrastructure, relied on long-span bar joists and insulated metal decking that was continuously welded and mechanically fastened in overlapping sections. Poured-in-place concrete slabs were installed in phased pours using laser screeds and power trowels, with specific areas designed for extra load-bearing capacity to support heavy machinery, battery cell stacks, and chemical storage zones. Critical to the operation of a battery manufacturing facility is the implementation of clean room environments and dry room chambers. These required building envelopes with extremely low air permeability achieved through multi-layer vapor barriers, continuous insulation, and air-sealed panel joints. Mechanical systems included desiccant dehumidifiers, HEPA filtered positive pressure ventilation, and redundant HVAC loops to maintain both particulate and moisture control. Specialized coatings were applied to floor slabs in clean areas, often involving epoxy resin with anti-static properties to protect sensitive electronics and prevent electrostatic discharge during cell handling. Power distribution infrastructure had to be scaled for high-load operations with on-site substations, high-voltage switchgear, and transformer yards designed to support continuous production. Bus duct systems and flexible conduit networks were installed overhead to provide modular electrical service to production lines, allowing for equipment reconfiguration with minimal downtime. Simultaneously, process piping systems for chilled water, nitrogen, compressed air, and vacuum services were routed through prefabricated utility racks mounted to steel columns. Environmental compliance was a significant design driver. The facility integrated stormwater detention basins, zero-discharge process water recycling, and volatile organic compound filtration systems to meet both federal and state environmental standards. Fire suppression systems had to account for the unique hazards of lithium-based materials, requiring dry chemical suppression in certain rooms and foam-based systems in others, backed by an advanced detection network including thermal imaging and gas sensors. Before the first runway grading begins, the Southern Nevada Supplemental Airport is being conceived as a large-scale airfield designed to relieve pressure on the heavily used Harry Reid International Airport. The location, set in the Ivanpah Valley south of Las Vegas, drives much of the engineering approach. Planners must contend with desert soil conditions, high summer temperatures, and seasonal winds, all of which affect runway orientation, pavement design, and operational layouts. Initial site preparation would start with extensive grading to create level surfaces for runways, taxiways, and terminal areas. Given the scale of a major airport, this would involve moving millions of cubic yards of material, compacting subgrades, and stabilizing any loose sands to prevent future settlement. Dust control measures would be constant, with water trucks and soil binders deployed to meet environmental requirements and protect nearby communities from airborne particulates. Runway construction would follow FAA specifications for length, width, and load-bearing strength, accommodating large commercial aircraft such as wide-body jets. Pavement design would likely involve a layered structure of stabilized subbase, aggregate base, and high-strength Portland cement concrete capable of withstanding the concentrated loads from landing gear. Each slab would be doweled and jointed for load transfer and thermal expansion, with embedded lighting fixtures for night and low visibility operations. Taxiways and apron areas would be built to the same high standards, but with added flexibility for ground handling equipment, fueling operations, and aircraft maneuvering. Underground utilities, electrical conduits, fuel hydrant systems, water supply, and storm drainage would be installed in parallel with pavement work to avoid costly future excavation. The terminal complex would require deep foundations to support multi-story structures, as well as integration of baggage handling systems, passenger boarding bridges, and high-capacity HVAC systems to maintain comfort in extreme heat. Structural steel framing would provide large, column-free interior spaces, while exterior glazing systems would be engineered with solar shading to reduce heat gain. Air traffic control facilities would include a control tower with unobstructed sight lines over all airfield operations, supported by radar, communications equipment, and backup power systems for uninterrupted service. Support buildings such as maintenance hangars, fire and rescue stations, and cargo handling facilities would be strategically placed for rapid response and operational efficiency. Once operational, the Southern Nevada Supplemental Airport would be a fully integrated transportation hub, engineered from the ground up to handle high passenger volumes, large aircraft, and the demanding conditions of the Mojave Desert, while ensuring capacity for the region's growing air travel demands well into the future. Ralph C. Wilson Jr. Centennial Park is one of the largest public space construction projects happening along the Detroit River, transforming a long stretch of underused riverfront into a fully developed recreational and ecological landscape. The site covers about 22 acres on the west riverfront, between the Riverwalk and Rosa Parks Boulevard, and it's being built as part of the Detroit Riverfront Conservancy's plan to connect the entire riverfront into one continuous system of parks, trails, and plazas. The project began with major civil and environmental work. The site had a long industrial history, meaning much of the soil had to be excavated, remediated, and replaced to meet environmental standards for public use. Contractors removed old concrete pads, underground foundations, and utility remnants from past warehouse operations. New drainage and stormwater systems were installed beneath the park, designed to handle runoff naturally through bioswales and rain gardens. The grading work shaped the land into a series of terraces that gradually stepped down toward the river, creating both flood resilience and visual access to the water. One of the park's most complex features is the water garden, a large engineered wetland that filters stormwater before it reaches the river. This system uses a combination of gravel beds, native plantings, and underground piping to slow and clean runoff, reducing pressure on the city's combined sewer system. The water garden is framed by concrete retaining walls and walkways built on driven piles to resist movement from seasonal soil changes. Structural crews coordinated closely with landscape engineers to ensure that the system could withstand fluctuating water levels without disrupting the surrounding vegetation. The central gathering area, known as the Wilson Plaza, is designed as a concrete and steel-supported deck structure that can handle heavy pedestrian loads and event setups. Beneath the plaza are electrical and utility lines to support lighting, sound, and temporary staging for concerts or festivals. The plaza connects directly to the Detroit Riverwalk through wide ramps and stairs, making it accessible for cyclists and pedestrians coming from downtown. Another key element is the expansive playground, called the Delta Dental Play Garden, which incorporates large-scale climbing structures, slides, and water play features. These installations are anchored into reinforced concrete footings and surrounded by safety surfacing made of poured-in-place rubber. Adjacent to this is the Sport House Pavilion, a steel and glass structure that includes restrooms, storage, and a small cafe. The pavilion is built on a concrete foundation with structural steel framing and an extended canopy roof for shade. Along the waterfront edge, crews have reinforced the seawall and added riprap protection to prevent erosion from wave action. New walkways are being poured with exposed aggregate finishes for durability, and integrated LED lighting is installed throughout the pathways to provide visibility without overpowering the natural setting. Trees and native grasses are being planted in phased sections with irrigation systems tied into the park's water recycling network. The park's construction is highly coordinated with other ongoing riverfront work, including the nearby Joe Louis Greenway and the West Riverwalk extension. Because of its size and variety of components, work is divided among multiple contractors, with sequencing planned to allow landscaping, civil, and structural tasks to overlap efficiently. Tucked away in the mountains of Guizhou Province in southwestern China, there's a gorge so deep and narrow that sunlight barely reaches the river at the bottom for most of the day. And spanning this massive cut in the earth, high above the mist and cliffs, engineers are building something that almost defies belief: the Huajiang Grand Canyon Bridge. When complete, it will stand among the highest bridges ever built on the planet. A structure so tall that if you dropped a skyscraper from the deck, it would fall for seconds before touching the valley floor. The numbers behind it are staggering. The bridge deck will rise over 600 meters above the river, which means it's taller than most observation towers and higher than the top floor of the Shanghai Tower. To put that in perspective, imagine stacking 2 Eiffel Towers end to end. That's roughly the drop from the roadway to the canyon below. This kind of height doesn't just make for dramatic photos, it turns every stage of construction into a feat of courage and precision. Workers spend their days suspended hundreds of meters in the air, guiding steel cables, assembling segments, and balancing heavy machinery on platforms that hang in the clouds. The Huajiang Grand Canyon Bridge is part of a new expressway that will connect cities across Guizhou, one of China's most mountainous provinces. Historically, this region was isolated by its terrain, deep valleys, twisting ridges, and karst formations that make road building incredibly difficult. The bridge is designed to close one of the biggest gaps, cutting travel times from hours to minutes, and linking communities that once felt worlds apart. In a province known for its poverty and difficult logistics, projects like this aren't just about transport, they're about access, trade, and opportunity. Structurally, it's a suspension bridge, chosen because it's one of the few designs that can handle both the span and the height of the canyon. The main span stretches more than 1 kilometer across, supported by enormous cables that anchor into the mountains on each side. The anchorages alone are buried deep in concrete and rock, absorbing the colossal tension forces that hold the deck steady. Every component must withstand fierce winds, extreme temperature shifts, and the constant pull of gravity across an open void. Even the construction of the towers is an achievement, with cranes and scaffolding perched on cliffs that would make most people's legs shake just looking down. What makes the Huajiang project even more impressive is how it reflects China's relentless drive to conquer geography with infrastructure. Guizhou has become a global showcase for bridge engineering, home to more of the world's highest bridges than any other region. Each one seems to push the limits a bit further. Higher decks, longer spans, faster timelines. The Huajiang Bridge is simply the next leap in that sequence, proving that there's almost no terrain too challenging to cross. When it finally opens to traffic, drivers will glide across a stretch of road that looks like it's floating between mountains, with clouds drifting below and the canyon yawning far beneath. It's one of those places where engineering and nature meet in a way that's both awe-inspiring and humbling, a reminder of what human ingenuity can achieve when the landscape dares us to go higher. High in the Colorado Front Range, nestled against the backdrop of the Rocky Mountains, the construction of the Chimney Hollow Reservoir unfolds as a feat of modern engineering designed to address long-term water storage and supply challenges. This reservoir, when completed, will serve as a crucial component of the Windy Gap Firming Project, tasked with ensuring a reliable water supply to over a dozen municipalities and water districts. The reservoir is not a natural formation, but a carefully engineered off-channel storage solution, meaning it is not built directly on a river, but instead captures and stores water piped from elsewhere, in this case, from the Colorado River, through the existing Windy Gap infrastructure. The site preparation phase began with intensive geotechnical surveys to confirm the structural integrity of the valley where the dam would be located. Crews cleared vegetation, regraded access routes, and constructed temporary diversion channels to handle stormwater runoff during the construction process. An essential early task involved excavating unsuitable soil and rock from the dam footprint, replacing it with engineered fill to provide a uniform foundation capable of supporting the massive weight of the structure. The dam itself is a rockfill embankment design with a central clay core, a choice made for its flexibility and impermeability. The clay core serves as the primary barrier to water seepage and is compacted in thin lifts using specialized rollers to ensure density and homogeneity. This core is flanked by transition zones of sand and gravel, which in turn are bordered by larger rockfill shells. These outer shells provide structural stability and protect the inner components from erosion and seismic activity. The rock used for the dam is sourced from on-site quarrying operations, which reduces the environmental footprint and transportation costs. A significant engineering challenge in this project involves the hydraulic structures that regulate the inflow and outflow of water. An intake tower, constructed with reinforced concrete, rises vertically near the upstream face of the dam, equipped with multiple inlets at varying elevations to allow selective withdrawal of water depending on quality and temperature needs. Connected to this intake is an outlet tunnel bored through bedrock, reinforced with steel liner sections and anchored against hydrostatic forces. In parallel, crews are constructing an upstream reservoir rim lined with a composite geomembrane to minimize seepage losses. This liner is protected with layers of cushion material and rock ballast to guard against mechanical damage. The dam crest will support an access road and monitoring equipment, including piezometers and inclinometers embedded within the dam body to detect any movement or internal pressure changes over time. Environmental mitigation measures are ongoing throughout the project. These include fish passage improvements elsewhere in the watershed, wetland restoration, and extensive erosion control using sediment basins, wattles, and hydroseeding on disturbed slopes. All construction activities are sequenced with seasonal weather patterns in mind, avoiding critical wildlife periods and minimizing impacts during spring runoff and winter freeze-thaw cycles. Every aspect of the Gordie Howe International Bridge's construction showcases the intricate interplay between transnational coordination, advanced structural engineering, and logistical execution at a scale rarely attempted in modern infrastructure. Spanning the Detroit River and connecting Detroit, Michigan with Windsor, Ontario, this cable-stayed bridge is designed to support massive volumes of commercial and passenger traffic, requiring not only the longest main span of any cable-stayed bridge in North America, but also a level of precision in its execution that leaves no room for error. The construction began with extensive geotechnical investigations on both riverbanks. Drilling rigs bored deep into the soil and bedrock to analyze subsurface conditions, as the design called for massive pylon foundations to be embedded securely below the frost line and into competent strata capable of bearing immense vertical and lateral loads. These foundations were formed using deep caisson shafts, reinforced with high-density steel cages and tremie concrete placed underwater to displace slurry and avoid cold joints. Each tower foundation supports a pylon rising hundreds of feet above the river, built incrementally using a climbing formwork system that allowed for the continuous casting of reinforced concrete without the need for external scaffolding. The bridge deck, a post-tensioned concrete and steel composite structure, was constructed in segments using balanced cantilever methods. Each deck segment was either precast off-site and transported by barge or cast in place atop temporary platforms extending from the pylons. As the main span grew outward toward the center of the river, temporary stay cables were anchored into the pylons and attached to each newly added segment. These cables, arranged in a fan pattern, were tensioned precisely using hydraulic jacks to counteract gravitational sag and to distribute structural loads symmetrically across both sides of the pylon. The stay cables themselves consist of high-strength steel strands encased in corrosion-resistant sheathing, anchored into massive anchor blocks within the pylon shafts. Vibration dampers were installed at intervals to mitigate wind-induced oscillations and ensure long-term fatigue resistance. Behind the structural work, the installation of intelligent transportation systems, roadway lighting, drainage infrastructure, and barrier systems proceeded concurrently. A crucial aspect of the bridge's construction involved integrating border control and inspection facilities on both sides, meaning the project had to encompass not just the main span and approaches, but also expansive landside infrastructure. These included customs plazas, inspection booths, weigh-in motion sensors, and secondary screening areas, all built to exacting standards set by two national governments. Coordination across these parallel construction zones required synchronized project management, shared construction specifications, and harmonized safety and environmental protocols. Cross-border utility integration further complicated the process. Power, water, data, and fiber optic lines had to be laid in conduits embedded within the bridge deck, secured and protected against temperature fluctuations, dynamic load stress, and electromagnetic interference. Weather posed another challenge. Extreme temperature swings, high wind exposure during deck segment installation, and ice buildup along the river all required constant monitoring and adaptive construction scheduling. With a total length extending over a mile and traffic capacity tailored for future expansion, the Gordie Howe International Bridge is not simply a physical connection between two cities. It represents a structural embodiment of modern binational cooperation and the evolving science of long-span bridge engineering, where every bolt, cable, and foundation element plays a precise role in maintaining stability, durability, and flow across one of the continent's most critical commercial corridors. From the earliest stages of planning, the construction of the Venetian in Las Vegas was envisioned as both a large-scale hotel and a themed architectural reproduction of Venice's iconic landmarks, requiring careful integration of structural engineering with elaborate facade detailing. The project began with deep foundation work, as the sheer height and footprint of the resort demanded a robust support system. Pile foundations and reinforced concrete mat slabs were installed to distribute loads evenly across the variable desert subsoil, with strict tolerances to accommodate the superstructure's alignment. The main tower and podium levels were built using a reinforced concrete frame for strength and fire resistance, while structural steel was introduced in key areas to allow for larger spans and open interior spaces, particularly in the casino floor and grand lobby. This combination of materials provided both rigidity and flexibility in meeting design requirements. The building envelope had to be engineered to withstand the extreme heat of the Mojave Desert while supporting ornate architectural elements, stone cladding, decorative moldings, and replicas of Venetian arches and columns, without compromising structural integrity. Mechanical, electrical, and plumbing systems were integrated early in the superstructure phase to serve the massive volume of rooms, retail areas, restaurants, and entertainment venues. High-capacity HVAC systems were distributed through mechanical floors, with ductwork routed in concealed chasers to maintain the interior's thematic authenticity. Plumbing networks were particularly complex, supporting not only the thousands of guest rooms, but also the extensive canal and fountain systems that define the property's public spaces. The Grand Canal itself required specialized water engineering. A reinforced concrete basin lined with waterproof membranes was constructed to hold the waterway, while concealed pumping and filtration systems kept the water clear and flowing. Load calculations for pedestrian bridges and canal-adjacent structures ensured both safety and the realistic aesthetic of Venetian streetscapes. Interior fit-out work was equally intricate. Large expanses of stone flooring, decorative plaster ceilings, and imported materials were installed with a combination of modern fastening methods and old-world craftsmanship techniques. Lighting systems were carefully tuned to highlight architectural details and simulate the soft ambiance of Venice, while still meeting safety illumination standards for a high-occupancy building. As the final stages progressed, the integration of themed architectural features with state-of-the-art hospitality infrastructure made the Venetian a unique challenge from an engineering standpoint. When completed, it stood not only as a luxury destination, but also as a highly complex, large-scale building system disguised beneath a meticulously crafted facade that captures the essence of its namesake city. It's not every day you see a desert city trying to rewrite the global skyline, but that's exactly what's happening in Riyadh right now, as the Rise Tower begins to take shape. Planned to reach over 450 meters into the air, this soaring structure is meant to become the tallest building in Saudi Arabia's capital, and one of the tallest in the entire Middle East. But more than just height, Rise Tower is about a statement, one of ambition, reinvention, and a new kind of identity for a city that's transforming faster than most people realize. What's striking about this tower isn't just the glass and steel, it's the setting. Riyadh has always been a low-slung city built to survive the desert, a place of wide roads and sprawling neighborhoods. But Rise Tower is breaking that mold completely. It's anchoring the King Abdullah Financial District, a mega project that's aiming to turn the city into a global hub for finance and innovation. With futuristic architecture, high-tech infrastructure, and walkable urban design, right in the middle of the desert heat. Now, designing something this tall in Riyadh isn't as simple as copying a blueprint from New York or Shanghai. The tower has to deal with harsh sunlight, extreme heat, and powerful desert winds. So everything from its orientation to its skin is being engineered to handle those forces. Think of deep shading fins, high-performance glass, and an internal cooling system that helps balance comfort with sustainability. It's a blend of modern high-rise engineering and climate-specific design, and it has to work flawlessly to support not just offices, but residences, hotels, and observation decks stacked layer after layer up into the clouds. But there's also a symbolic layer to this. Rise Tower isn't just an office building with a fancy spire. It's part of a broader push to redefine what Saudi cities can be. It's coming at a time when the country is pouring trillions into development projects, from NEOM to Diriyah. And Riyadh is being positioned as a global destination in its own right. So when you build a tower like this, you're not just constructing floors and elevators. You're constructing a future image, something that says, this is who we are now. And the engineering muscle behind it is just as intense as the vision. You've got mega piles drilled deep into the desert floor to support that much vertical load. You've got cranes operating at dizzying heights in a climate where metal burns to the touch by midday. Logistics, labor, safety, it's all being choreographed at a massive scale to keep everything on track. Because once you start reaching that high, every little mistake becomes a very big problem. Central 70 project in Denver represents one of the most complex and transformative infrastructure undertakings in Colorado's transportation history, fundamentally reconfiguring a critical 10-mile stretch of Interstate 70 through the heart of the city. At the core of the effort was the removal of the aging viaduct structure that had long carried the interstate above the Elyria-Swansea neighborhood. This steel and concrete elevated section had deteriorated over the decades, and replacing it with a lowered, modernized alignment required not only intense engineering, but also delicate coordination with the surrounding urban environment. The initial phase focused on relocating utilities, a task complicated by the dense urban fabric and the age of existing infrastructure. Contractors rerouted water mains, sanitary and storm sewers, gas lines, and electrical conduits, many of which had limited documentation. Horizontal directional drilling and jack and bore techniques were employed beneath active roadways and rail lines to avoid surface disruption. Simultaneously, temporary roadways and detours were constructed to shift traffic off the viaduct while demolition proceeded. One of the most technically demanding aspects was the excavation of the lowered section, which required removing hundreds of thousands of cubic yards of earth to create a trench deep enough to carry multiple lanes of traffic, including managed lanes. Retaining walls made from cast-in-place concrete and mechanically stabilized earth were built along both sides of the corridor. These walls were engineered with integrated drainage systems to handle both surface runoff and groundwater, preventing hydrostatic pressure buildup behind the structures. A significant centerpiece of the project was the construction of a 4-acre park over the sunken interstate near Swansea Elementary School. This cap structure was designed using post-tensioned concrete girders and a robust waterproofing membrane system to ensure long-term durability above the active highway. The park's substructure also included passive ventilation systems and emergency egress points for the roadway below. During this phase, noise and vibration monitoring were continuously conducted to minimize the impact on the adjacent school and residential areas. Traffic flow improvements extended beyond the trench. The project reconfigured interchanges, widened shoulders, and introduced express toll lanes in both directions. To construct these elements within tight right-of-way limits, crews often worked in staggered shifts, utilizing night closures for tasks like bridge girder placement and median barrier installation. Intelligent transportation systems, including overhead gantries, traffic cameras, and variable message signs, were embedded into the corridor to enhance incident response and traffic management post-construction. Stormwater management was also a major design consideration. A new pump station and series of underground detention basins were built to handle flood conditions, especially given Denver's susceptibility to intense summer thunderstorms. These systems were integrated with oil-water separators and filtration units to ensure runoff met environmental quality standards before discharge. Rising from the ground in Ann Arbor, Michigan, Michigan Stadium, affectionately known as the Big House, stands as a monumental achievement in sports architecture and large-scale civil engineering. Built originally in 1927, this colossal arena was constructed using reinforced concrete and steel framing, foundational techniques standard for the era, but scaled to accommodate a capacity rarely attempted at the time. The original bowl-shaped design was partially excavated below grade, taking advantage of the natural topography to reduce the visual impact of such a massive structure while simultaneously stabilizing the stadium using earthen berms. These berms supported precast concrete seating risers, anchored by poured-in-place footings and beams interconnected with structural steel. The construction process required meticulous planning around soil stability and drainage. Because Michigan's weather delivers both intense snowfall and summer storms, underground drainage channels and weeping tile systems were embedded early into the substructure, designed to manage both runoff and groundwater intrusion. The initial playing field was situated well below street level, necessitating a highly efficient sub-drainage system beneath the turf to prevent waterlogging during peak precipitation events. Over the decades, Michigan Stadium underwent several massive renovations and expansions, each posing unique engineering challenges. The most significant overhaul occurred between 2007 and 2010, when the facility saw the addition of permanent luxury boxes, widened concourses, upgraded utilities, and seismic retrofitting to bring the structure closer to modern code compliance. That project required the integration of new vertical loads into an old horizontal system. Steel columns had to be carefully inserted through the existing bowl structure using micropiling techniques and strategically placed caissons to avoid overloading the original foundation elements. Simultaneously, workers installed reinforced concrete cores for elevators and stairwells without disturbing the stadium's operational calendar. Upgrading the seating capacity to over 100,000 spectators also required detailed structural modeling to ensure the new steel and concrete additions harmonized with the older materials. Engineers conducted ground-penetrating radar surveys and core samples to map existing subsurface conditions before extending load paths downward. The press box and suite levels introduced additional dead loads, managed using a combination of cantilevered steel trusses and post-tensioned concrete slabs. To reduce long-term settlement and dynamic sway, vibration-damping devices were installed beneath critical sections. Electrical and mechanical systems, completely overhauled during the renovations, were modernized with distributed load centers, LED lighting infrastructure, and integrated HVAC modules. Chilled water loops and forced air ventilation units were retrofitted within the confined voids beneath the seating to maintain thermal control during shoulder seasons. Coordination between MEP subcontractors and structural teams was essential to route utilities through structurally sensitive zones, often requiring three-dimensional clash detection software during the design phase. Spread across a vast expanse of desert terrain in southern Nevada, the Copper Mountain Solar Complex represents a large-scale application of photovoltaic technology built in multiple phases to steadily increase generation capacity. Each expansion began with extensive site grading, where bulldozers and graders prepared the ground to ensure uniform slopes for drainage, while preserving the structural stability needed to anchor thousands of solar panel arrays. Given the desert environment, dust suppression was a continuous concern during earthwork, requiring water trucks to regularly dampen surfaces without creating erosion. The mounting system for the panels was engineered for both durability and precision alignment. Steel support posts were driven into the compacted soil using pile-driving rigs equipped with laser-guided systems to ensure exact placement. The arrays were organized in long, continuous rows to maximize exposure to the sun's path, with spacing calculated to prevent self-shading at low solar angles in winter months. In some phases, fixed tilt mounting was employed for simplicity and low maintenance. In others, single-axis tracking systems were installed, allowing panels to pivot slowly from east to west over the course of the day to capture more energy. Photovoltaic modules were lifted and positioned by crews working from specialized installation vehicles, their wiring connected in series and parallel configurations to form electrical strings. These strings fed into combiner boxes, which consolidated current before routing it through underground conduit to inverters. The inverters, housed in weatherproof enclosures, converted the direct current from the panels into alternating current, suitable for the grid. Electrical infrastructure was scaled to match the plant's increasing capacity. Transformers stepped up the voltage for transmission, and switchgear assemblies coordinated power flow to the utility interconnection point. Because of the extreme heat, electrical components were designed with thermal derating considerations, and ventilation or shading was integrated to protect sensitive equipment. Maintenance pathways were built between panel blocks, allowing access for inspection vehicles and crews. Vegetation control was minimal due to the arid climate, but the site design included erosion control measures at drainage points to protect both the panel foundations and access roads during sudden rainstorms. Buried deep in the mountains of southeastern Tibet, there's a river that carves through some of the most rugged terrain on Earth, twisting and falling through a gorge deeper than the Grand Canyon, with more raw untapped power than almost any river in the world. This is the Yarlung Tsangpo, and right near the remote county of Meadog, China is planning something that could change the entire energy equation of Asia. A hydroelectric project so enormous, so ambitious, and so politically charged that it's hard to believe it's even real. Now, what makes this project so unique isn't just the size, although that alone is staggering. The Meadog hydropower project is being planned to generate more electricity than even the Three Gorges Dam, which is already the largest power station on Earth. If completed, it would produce somewhere in the ballpark of 60 gigawatts, enough to power entire nations, by harnessing the incredible natural drop of the river as it plunges through the world's deepest canyon. And the wild thing is, it's not some slow, meandering descent. The Yarlung Tsangpo crashes down thousands of meters in a short span, creating a perfect scenario for ultra-high head hydroelectricity. But the challenges here are just as intense as the engineering dream. First off, the terrain is basically vertical. This region is remote, landslide prone, and regularly battered by extreme weather, not to mention earthquakes. Transporting materials and equipment up here means cutting through one of the least accessible areas in China, which in itself becomes a construction project the size of a mega project. And then there's the environmental question. Meadog sits in one of the most biodiverse and fragile ecosystems in the Himalayas. Dam the river here, and you don't just affect a local valley, you impact everything downstream, from Indian states to Bangladesh, who rely on this same water flowing through their farmlands. Which brings us to the other layer, geopolitics. India sees the Yarlung Tsangpo as the upper reach of the Brahmaputra River, which feeds millions of people downstream. So when China talks about putting a giant dam across this section, it sets off alarms. Water security, strategic control, ecological disruption, it's all wrapped into one enormous and highly sensitive project. Yet for China, the prize is irresistible. A clean energy source of that magnitude, generated inside its own borders, could be a cornerstone for reaching its carbon neutrality goals and reducing its reliance on coal. And beyond all the politics and environmental concerns, there's the engineering itself. Imagine building tunnels and intake systems through rock that's constantly shifting, where just getting workers to the site takes hours over winding cliffside roads, and every drop of rain could trigger a mudslide. It's not just about pouring concrete and installing turbines, it's about reshaping an entire mountainside, building under conditions where nature constantly pushes back. Vegas Strip, the T-Mobile Arena was conceived as a multi-purpose venue capable of hosting everything from championship hockey to high-profile concerts. Its construction demanded a compact, vertical approach to fit within the limited site footprint, while still accommodating seating for tens of thousands of spectators. Engineers began with a deep excavation for the foundation, where reinforced concrete pile caps and spread footings supported the load of the superstructure. The subgrade preparation included soil stabilization measures to counteract any settlement in the alluvial deposits common in the area. The arena's structural system is a hybrid of reinforced concrete for the lower bowl and steel framing for the upper tiers and roof. Massive steel trusses were fabricated off-site, then transported in segments and lifted into position using crawler cranes with high lifting capacities. These trusses form the backbone of the long-span roof, which was designed to eliminate interior columns that could obstruct views. The roof decking incorporated acoustic insulation and energy-efficient membranes to regulate interior climate and reduce noise transmission. Exterior cladding was chosen both for aesthetics and thermal performance. The facade combines glass curtain walls, metal panels, and shading fins to break up the building's mass while controlling solar gain. The curtain wall system was engineered to withstand high wind loads while maintaining clarity and transparency, allowing the glow of interior lighting to become part of the strip's nighttime skyline. Inside, the seating bowl was designed with steep rakes and precisely calculated sight lines to keep spectators close to the action. Concrete risers and precast seating elements were installed in phases, coordinated with mechanical, electrical, and plumbing rough-ins that run beneath the concourse floors. The MEP systems themselves were scaled to handle large surges in occupancy, with high-capacity HVAC units, robust fire suppression systems, and redundancy in electrical feeds to maintain operations during events. One of the more complex phases involved installing the event flooring systems. For ice hockey, a network of embedded refrigeration pipes circulates glycol solution beneath the slab, allowing rapid ice formation. For concerts or basketball, modular floor panels cover and protect the ice while providing a stable surface for staging. The final phase focused on integrating technology and finishes. Advanced LED ribbon boards, a high-definition center-hung scoreboard, and distributed audio systems were installed alongside premium seating areas, luxury suites, and public concourses finished with durable, easy-to-maintain materials. When completed, the T-Mobile Arena became not just a venue, but a highly engineered piece of infrastructure designed for flexibility, efficiency, and the high demands of Las Vegas non-stop entertainment environment. Beneath the W Marriott Detroit Water Square Hotel is planned as one of the most prominent additions to the downtown riverfront, a large-scale luxury development that will anchor the area between the Renaissance Center and Hart Plaza. The project is part of the broader effort to reactivate the riverfront with high-density commercial and hospitality uses, replacing underused lots with new structures that tie the waterfront directly into the core of downtown. The hotel is designed as a modern high-rise, rising roughly 20 to 25 stories depending on final design adjustments, with several hundred guest rooms, meeting spaces, and a large podium containing restaurants, event facilities, and retail space. Structurally, the tower is built around a reinforced concrete frame with sheer walls that provide lateral stability against wind loads from the riverfront. The central core houses vertical circulation, elevators, stairwells, and mechanical shafts, while post-tensioned concrete slabs extend outward to form the guest room floors. This combination gives the building strength while keeping the floor plates thin and flexible for interior layouts. The foundation system along the riverfront is complex due to the soil conditions, which consist of deep layers of fill and soft sediment over older industrial material. Before vertical construction begins, crews install drilled shafts and concrete piles, reaching down to stable bearing layers. These piles support a thick concrete mat foundation that distributes the tower's load evenly. Because the site sits close to the Detroit River, groundwater control is also a major concern. Dewatering systems are installed during excavation to prevent water intrusion, and permanent waterproofing membranes are applied below grade to protect the structure. Once the foundation is complete, work proceeds with vertical concrete pours for the core and columns. The podium section is framed first, as it houses large open spaces like ballrooms and conference areas that require wider spans. Structural steel is often used in this part of the building to allow for column-free interiors. Above the podium, the tower floors are poured level by level using climbing formwork and tower cranes positioned along the site's north edge to avoid interference with the Riverwalk area. The facade design combines high-performance glass curtain walls with architectural metal panels and lightstone finishes near the base. The glazing system is chosen to resist high wind pressures from the waterfront exposure, while providing energy efficiency through insulated glass units and integrated shading devices. The lower levels facing the public plaza are planned with large transparent openings to connect indoor dining and lobby spaces to the outdoor pedestrian areas, while the upper floors are fully glazed for views over the river and into Windsor across the water. Inside, the JW Marriott will include full-service hotel amenities such as a spa, fitness center, multiple restaurants, and a rooftop lounge. Mechanical systems are distributed through central risers in the core, with separate zones for guest room floors and public areas to manage ventilation and temperature control efficiently. The building's mechanical plant is expected to use a combination of high-efficiency chillers and heat recovery systems to meet energy codes and reduce long-term operational costs. The surrounding site development at Water Square includes new pedestrian plazas, landscape features, and connections to the Detroit Riverwalk. Utility upgrades are being coordinated with the city's ongoing waterfront improvements, ensuring that stormwater management and electrical systems integrate smoothly with the public infrastructure. Set against the wide-open expanse of eastern Nevada, the Spring Valley Wind Farm was developed to capture the region's steady wind resources and convert them into utility-scale electrical power. Building such a facility began with a detailed wind resource assessment using meteorological towers to gather multi-year data on wind speed, direction, and turbulence intensity. This information guided the precise placement of each turbine to maximize efficiency while minimizing interference between units. Before installation could begin, the site underwent grading and road construction. Access roads had to be engineered for heavy transport loads, as turbine components, blades, towers, and nacelles are among the largest and heaviest pieces of equipment moved over land. The roads were designed with gentle curves and controlled gradients to accommodate the specialized trailers used for hauling blades that can span well over 100 feet in length. Foundations for each turbine required deep excavation to reach stable soil strata, followed by the placement of reinforced concrete pads. The circular foundations were heavily reinforced with steel rebar cages designed to resist overturning forces generated by wind loads on the tower. Anchor bolt assemblies were precisely positioned to match the base flange of the tower sections. After concrete placement, a curing period ensured that the foundation reached its full design strength before tower erection began. The tower installation process was conducted in segments, typically 3 to 4 cylindrical steel sections lifted into place by high-capacity crawler cranes. Precision alignment was critical, with each section bolted and tensioned to exact torque specifications. Once the tower was complete, the nacelle, housing the gearbox, generator, and control systems, was hoisted to the top. Blade installation was one of the most technically challenging steps, often requiring calm weather conditions for safety. Each blade was bolted to the hub, and the completed rotor assembly was lifted and attached to the nacelle's main shaft. Electrical cabling inside the tower connected the generator to underground power lines, which routed energy to a substation. At the substation, transformers stepped up the voltage for transmission over long distances, and control systems monitored the performance of each turbine in real time. Data from sensors on the nacelle and blades fed into a centralized control center, allowing operators to adjust blade pitch and yaw to optimize energy capture. When fully operational, the Spring Valley Wind Farm stood as a coordinated network of mechanical and electrical systems, engineered to operate reliably in the region's unique wind patterns and contribute clean, renewable power to Nevada's grid for decades to come. Situated in downtown Detroit, the Hudson Site development is one of the most technically ambitious construction projects the city has seen in decades. It occupies the block where the old J.L. Hudson department store once stood, and it's being transformed into a two-building complex that combines a high-rise tower with a shorter podium structure. Together, they'll hold offices, residential units, a hotel, restaurants, and event spaces, forming a new commercial and cultural center right on Woodward Avenue. The taller tower is planned to reach around 680 feet, which would make it one of the tallest buildings in Michigan. It's built around a reinforced concrete core that houses elevators, stairwells, and mechanical systems, with structural steel framing extending outward to support the floor plates. The shorter building along the northern side of the site is made up of concrete slabs and steel framing as well, but its layout is more horizontal, designed to handle large crowds for exhibitions and retail activity. The foundation work on this project was a major operation. Crews excavated deep below street level to remove old building debris and create space for several basement levels that will house parking and utilities. Piles were drilled down to bedrock to provide stability for the heavy superstructure above. Once the foundation was in place, a tower crane was installed near the center of the site to handle the lifting of steel beams and precast panels. In the later stages, a climbing crane was attached to the building's core to continue lifting materials as the structure rose higher. Because the site is located right in the middle of downtown, logistics have been one of the toughest challenges. There's very little room for material staging, so everything from rebar to glass curtain wall panels arrives on a strict schedule. Deliveries often happen at night to avoid disrupting daytime traffic. Concrete pours for the core were done in sections, with slip forming used on some parts to maintain a steady pace. The sequencing had to be carefully planned to keep trades working continuously without getting in each other's way. The exterior facade combines glass, metal, and stone panels that are designed to reflect both modern architecture and the historic look of downtown Detroit. Each curtain wall section is prefabricated off-site and lifted into position by crane. Behind the facade, mechanical systems for heating, cooling, and electrical distribution are integrated floor by floor as the building rises. Interior work starts from the lower levels once the upper floors are sealed in, with framing, drywall, and mechanical installations progressing upward in stages. As of now, much of the tower's structural frame is complete and interior finishing is underway. The shorter podium structure is further along, with glass and exterior cladding mostly installed. When the entire project is finished, it will contain hundreds of thousands of square feet of mixed-use space and serve as a key part of downtown Detroit's ongoing redevelopment. The engineering precision, tight scheduling, and vertical construction methods used on the Hudson site reflect the scale and complexity of rebuilding a major urban core. Exchange Detroit is one of the most technically distinctive construction projects in the city, mainly because of how it's being built. Located in the Greektown district, near the heart of downtown, this mixed-use residential tower stands out not only for its appearance, but for the method behind it, which uses a modular steel system that allows the building to rise from the top down instead of the conventional bottom-up approach. The project sits on a tight urban site, bordered by active streets, so the design had to minimize on-site congestion while still allowing vertical construction. The developers and engineers adopted a lift-build system known as lift build, which is rarely used in the United States. The process begins with the central concrete core being constructed first, housing elevators, stairs, and utilities. Once that core is complete, the building's individual floor plates are assembled on the ground, complete with structural steel, floor decking, and even some interior framing. Each completed level is then hydraulically lifted up the core and locked into position. This top-down assembly approach dramatically reduces the need for exterior scaffolding and cranes moving materials to upper floors. It also shortens the construction schedule because teams can prepare multiple floors on the ground simultaneously while the lift system raises them in sequence. The floors are connected to the core using steel collars and tension bolts that secure each slab permanently in place. The precision required is extremely high. Every lift operation must keep the floor level within fractions of an inch to ensure the structure aligns correctly. The Exchange Detroit Tower reaches around 16 stories and includes residential units on the upper levels with commercial and retail space near the base. Its structure combines a concrete core with a steel frame, and once the main lifts were completed, work shifted to the facade installation. The exterior system uses prefabricated curtain wall panels that attach directly to the steel framing, featuring glass and metal finishes that give the building a sleek vertical look. The curtain wall sections are brought in ready to install, reducing the time crews spend working at height. Inside, the residential floors are laid out with modern apartment units that were framed and partially fitted before lifting. Mechanical, electrical, and plumbing systems are routed through pre-coordinated chases in the core, with connections made once each floor is set in place. Because so much of the building was prefabricated, interior fit-out could move faster than in a conventional tower, with drywall, flooring, and finishes following immediately after structural completion. The foundation of Exchange Detroit is a reinforced concrete mat designed to support the concentrated load of the core and the steel floors attached to it. The mat rests on deep caissons drilled into stable soil below the downtown subgrade. From an engineering perspective, one of the biggest challenges has been sequencing. Every stage, from ground assembly to lifting, has to follow a strict order since the structure can't be adjusted afterward. The